All right, so I will put you to sleep for the rest of the day then, yes? We have a whiteboard, good. Whiteboards, do we have a whiteboard here? In case I need to write something.
Yeah.
Just in case.
Yeah, of course.
Better to get ready ahead of time. Good, and that's plenty. I probably won't need it, but it's always better to be ready. Just in case. Good. All right. This. So you're in charge. When you tell me when it's time, here's the important thing. You have to tell me when to start and stop, because I don't keep track of time.
I'll take care.
And I will just talk continuously.
Don't worry.
Okay. We'll try to, I know you want to do a break partway through.
morning to all of you.
There you go.
Very good morning to all of you. And I'm very happy today because this is a workshop which is under IOE initiative. And we have a special guests from US, Dr. Nestor. And Dr. Nestor is well known, but in the interest of audience, let me introduce briefly. Actually, I have about 6 pages of CV. I'm not going to read out everything. But let me just briefly tell you about his background. Dr. Nestor obtained his PhD from University of Illinois, Argonne in 1978. And he has been the senior scientist of microscopy in Argonne National Lab from 2005 till date. And he's also a scientific director and group leader, Electron Microscopy Center from 1984 to 1994. And he's also a scientist in Electron Microscopy Center from 1983 to 2005. And he's also an engagement in Oak Ridge National Lab from 1978 to present. And he has got several university appointments. I'll just mention a few of them. He's a senior fellow, Consortium for Advanced Science and Engineering, University of Chicago from 2018 to till date. And he's a senior fellow from Northwestern Argonne Institute for Science and Engineering. And he's also a senior fellow of Computational Institute, University of Chicago. And he's also visiting professors, positions in several universities, importantly, University of Manchester, Northern Illinois University, University of Illinois at Chicago, Cambridge University, Urbana-Champaign, and Illinois Institute of Technology in Chicago. So, Dr. Nestor has got several professional honors and awards. The list is quite long, and I'm not going to read everything.
Good. You could stop there.
And some of them, with the latest ones, at least I'll mention, in 2023, he has been recognized with the David Cockheim AMMS Award and Guinness World Record Award in 2022. And almost every year he has got an award. So it's a very illustrious career, and I'm extremely happy and privileged that he is here to conduct this workshop. And thank you, Dr. Nestor. The floor is yours. Maybe I'll request Ravi to share a few words, because he is also, he can mention about our institute initiative about this, so that we could do all this.
Dr. Shankaran, thank you. Thank you very much. Thank you very much for bringing Dr. Nestor here, and I'm told in the afternoon Dr. Hamish Fraser also will be here. It's a pleasure to have you, Dr. Nestor. You must be knowing that IIT Madras has heavily invested in microscopy, electron microscopy, and we have state-of-the-art characterization facilities in the institute. Yes. And electron microscopy is being led by Dr. Shankaran. Oh, certainly we have a lot of interest in electron microscopy, and IIT Madras was named as an Institute of Eminence by the Government of India. And that scheme, several centers were approved. And one of the centers that were approved to be established is an Institute of Eminence Center on Electron Microscopy, Advanced Microscopy. Mm-hmm. So he has invited you under that center to offer lectures. So we are very happy that he has brought some esteemed and highly qualified people who can engage the students with basic concepts to advanced concepts in microscopy. I think I don't have to say much, because when you started your microscopy career, I was just a 3-year-old baby opening up my eyes to see how the world looks like. So I think you have phenomenal experience in
Markham.
Yeah. But if it is that, then mine is much smaller at a nanoscopy scale. So I would welcome you once again. So I hope you will have a nice time interacting with the students here. And we will meet again in the afternoon after my class. I'm teaching right now, so I will meet you again.
Better get going.
I'll do that.
Nanrai.
Yeah.
Thank
you.
Vankanam. Thank you again, everyone. It's my pleasure to be here. It's my pleasure to return to IIT, because I got my bachelor's degree at IIT. IIT in Chicago, not IIT in Madrid. Slightly different name, but the initials are the same. So, today is going to be an interesting day. As I was telling everybody a few moments ago, this is a workshop. It's not a lecture. I'm not here to just talk to you. I will. But the important thing, and maybe even for our remote audience, can they send in questions, email you? Okay, if you have a question, you should stop me and ask the question, okay? Because if you have a question, it needs an answer. If it's a really long question, maybe we'll put it off for a little bit, but if relatively short questions or something, a clarification, we should do that. The challenge that I have is to try to cover a lot of material in just 2.5 days. We will not succeed, okay? To tell you that ahead of time. But everything that I present today will be available as a PDF that I'll give to with it, and you can all have a copy of it, okay? It will all be public domain information. You can share it both for your own notes and share it with colleagues, okay? So, just to give you a sense of what we're going to talk about first, let's see if my thing, I'm going to go backwards for a moment. So what we're going to talk about today is a variety of things. I'm going to start talking first in general about EM in general and materials, just to give you a few examples of the kind of things we do. Then, because we've got a wide audience here, some of you know electron microscopy fairly well, other yous need a refresher, and some people will be novices. So I'm going to spend some time talking, let's see if I can use this. Does this work? Yes. We'll talk first a little bit about challenges and some examples and materials, and then I'm going to talk about the basic instrumentation. Okay? My purpose is the following. If you don't understand the basic instrumentation, then you don't understand how to use it to solve different problems. I don't want you to go away today or this week and just say, all I have to do is push a button and I'll get an answer. If that's the message you get, I failed. The message today is let's understand how we detect something, how we measure something, and then how we analyze the data to get quantitative results to answer a question. The important thing is, what's the question you're trying to ask? How do we then make a measurement to get the answer to that question? What resources are needed? And what experiments might you need to do to answer that question? Now, during the course of the next few days, we're going to talk about a lot of different techniques. It's not just an electron microscope. What we have in reality is an instrument that I call an electron optical beamline. Those of you know about beamlines at synchrotrons, right? A microscope is no different. There's a source, an accelerator, optics to bring a beam to a target, scattering from the target, and detectors that surround it. It's a beamline. And some of our beamlines, modern electron microscopes, are actually cost as much as a normal beamline in a synchrotron. Their beamlines are fairly simple. It's just a straight tube with a beam. We have a lot more complicated factors to deal with. All right. Then after lunch, we're going to talk a little bit about electron diffraction first, or diffraction phenomena. I'll start it off, and then Hamish will jump in and add some more. Tomorrow, we'll talk about elastic scattering, mainly imaging, okay? Both conventional TEM and scanning transmission, and dynamical theory and diffraction contrast, some imaging. After lunch, I'll talk about inelastic scattering, which is actually my forte, the thing I get most interested in, and how we use inelastic scattering also to characterize our sample. Finally, in the last day, we're going to have some, depending on what the audience is interested in, we'll talk about other topics that we can add. Radiation damage, chemical imaging, in situ microscopy, different aspects. And I'll base that based on you. If nobody's here interested in situ, we won't talk about in situ. If you're interested in radiation damage, we'll do that. Maybe we can get Hamish to talk a bit on computationally mediated microscopy. All of that is relevant, so we'll play it by ear. And then in the end, we'll have an open question and answer session. And there, what I would like you to do is think about the work you're doing or the problems that you're trying to study right now and say, I have the problem. Here's my problem. What would you do? And we probably don't know the answers, but we can at least give you some direction. Okay, so let's move forward. First thing I want to do is obviously acknowledge I work at Argonne. Most of my work is supported by the US Department of Energy and at Argonne National Lab. I have a lot of colleagues that have contributed to a lot of the slides I've had over the years, and they make a huge list, okay? And I can't remember them all, because my slides I've been collecting for years, so. I thank them all, and I apologize to any of them on my list that I've forgotten to put their name down. Again, anybody wants a photo, those of you in the audience watching remotely, we are going to have the lecture notes. Every slide that I present over the next few days will be converted into a PDF, and you'll be able to get a copy of that, and you can share that. So it will be freely available. Okay, let's talk for a minute about materials research today. What do we do? What do we do? We're interested in new materials and phenomena. What we try to do is we create new things. We discover and explore to try to understand them. We control these materials, and we apply them to solve problems in today's society. What's our motivation? Well, there's a lot. There's also a national strategic need. Doesn't matter what nation you're in, everybody has a need to do something. We're all focused on energy and the economy today. Health is important. There is some work on defense for everybody. And really, the thing that gets me excited is not so much is enabling other science. What can I do to help somebody else to let them do their science? All of that is important today. Okay? Let's ask ourselves, what's the basic question that we all ask? Well, we ask ourselves, what does it look like? What's the state of the material? What's its morphology, its shape? Is it crystallographic? Is there crystallography involved? What are the elemental and chemical constituents of what we're looking at? Is there bonding? Can we tell some information about that? What's the electronic structure? It depends on the problem you're doing. We also have evolved. In the past, we did everything statically. We'd look at something and it was there. It was effectively dead, nothing moving. Today, that's no longer the problem. In today's evolved technological environment, we want to watch things dynamically. We want to see things change. We want to understand what's making the change. And what are those dynamic processes? Well, it could be just a change with time. Could be a change with temperature, stress or strain. Those of you that are mechanical engineering know quite a bit about that. We want to look at different environments. We don't want to look at things in vacuum. We don't exist in vacuum. Most materials don't. What happens when we change the environment? What happens when we put an electromagnetic field of some type on it? And is there an irradiation environment? And there's two reasons for radiation environment. It's not just nuclear materials. It's satellites in space. They're in an irradiation environment. We need to know what damage happens there. So that irradiation environment could be charged particles, could be photons, could be almost anything. And what are our challenges? The challenges today is to do all of this in real-time processes. We want to watch things happening. Let's see now. I think this guy should, if I push the button, there we go. Go. We want to watch things changing. We watch things moving. I want you to watch this process. These are actually particles in a liquid in the TEM. Okay? We watch particle growth, particle coalescence. We want to understand what's happening. And you can see not only are they moving, but they're coalescing, they're ripening, getting larger. How can we do that? We want to do high spatial resolution analysis, and we'll be talking about later in the week. We also want today to do simultaneous imaging of both hard and soft materials, polymers and metals, ceramics and biological materials. So all of that, knowing the relationship between those. We want to do it dynamically. What I'm showing you there, that little video clip was slow. We might want to do it faster because we want to watch a dynamic process that's happening rapidly, or maybe we want to do it slowly. Okay, so that's what we'd like to do. Now, what are the basic questions that most investigators ask? Well, they tend to ask, what does it look like? How big is it? Okay. What's it made out of? Where are the important bits? And I always get this one. That's not what I expected. It shouldn't look like that. Okay? So we want to watch things going on, and we want to explain that. Ask yourself, what are the limiting factors? So you have an opportunity here. One of the opportunities is the barrier to entry. Well, here at IIT Madras, you've got resources that are available for you to do that. So your barrier to entry is a little bit lower than somebody that doesn't exist at a university like Madras. There is some bureaucracy. You're going to have to do some paperwork. You have to be a student or a researcher. You have to find money to do it, or somebody has to find money to get the resources here. Nicely, the department's done that for you, or at least some of it. You need staff. It's not just you running the instrument. There's research staff associated with it that has to help you. You need access. You need the ability to get to it. And there are also barriers to getting results. Okay? The most important barrier to getting any result with any electron microscope, any investigation, make sure you know your specimen. You should be spending as much time understanding your specimen and making your specimen as you do everything else. Because in the US we have the saying, garbage in is garbage out. Okay? We need expertise. That's why you're here at the university, to get some expertise. You have the advantages of local experts that can help you to do things, and expert staff. And you need the infrastructure and instrumentation. And again, you've got some very nice tools here, resources, to do that. All right. What are today's challenges? I'll give you the big picture now first. I'm going to start out with the big picture, and then we're going to work around. The big picture is multimodal analytical sensitivity at the sub-nanometer to sub-angstrom resolution ladder in both hard and soft matter. So what do I mean by that? I mean, well, we're going to be looking at materials. Here's an example of a complex engineering material. It happens to be a catalyst. Actually, that's not the catalyst. That's the support. That's basically cerium oxide. The catalyst, if you can see them, they're small, very little tiny white dots there. That happens to be, and now you see them in red, the ruthenium, which is the catalyst. So the cerium oxide in blue is the support. The ruthenium in red is the catalyst, and that's the thing we're interested in. So how do we know where it's there? We have to use a subsidiary or other analytical processes to see them. It's not just catalysts. Everybody's worried about water today. Okay? This is a polyamide membrane. It's used in water filtration. What do filters do? They take out of the water contaminants. Okay? Can we see? Well, we see little things in here. Okay? This happens to be a complex folded membrane, and it's absorbing materials. How do we know it's absorbing? Well, we get these white areas. What are those white areas? Again, during the course of the day, we'll learn that those white areas can be analyzed, and we can tell that those happen to be transition metals that are acquired on the membrane surface. Biological systems. This is a photocatalyst to help convert CO to water, and from the water we get hydrogen and oxygen, so we got energy. Okay? This is a thacaloloid. Okay? It's from the surface of a cyanobacteria, which we find all around the world. These naturally take CO and convert oxygen, convert hydrogen, create water. What we want to do is enhance the productivity of it. We found out that if you add noble metals, in this case platinum, to the thacaloids, that the enhanced catalytic activity happens. Well, where does it go? Well, we see lots of white dots again. That we assume is platinum. Well, yes, can we see the platinum nanocrystals? Yes, we can see. If I blow a layer up like that, we see the platinum nanocrystals, but that's not the important thing. What's important are these tiny white dots, which are single atoms of platinum sitting there. Those are what's helping do the catalytic process. Okay, and at some cases, now that's supposed to be a video. Let's see if I can get that to work. Where is the button? Certainly in the machine you have here, the aberration-corrected imaging machine. This came from an aberration-corrected imaging machine. We're looking at the edge of a single crystal. And what do we watch? Oops. If we watch that, let's see if I can get it to play a second time. We see single atoms, and watch very closely, single atoms moving along that surface. What's happening there? Why are they moving? How do we get these images? How do we analyze that? That's some of the work we're going to be talking about here. Okay, and we want to do all of that in real time. And I'm sure all of you would say, oh, gee, I just want to make my sample, put it in a microscope, push a button, and get an image. That doesn't work, okay? If you don't understand the machine, the technique, all you're going to do is waste your time and waste time on the instrument. So I'm going to spend a lot of time talking about the instrument so you understand it, techniques to use to understand the images you, and then toward the end we'll talk about how we analyze the data. So I will spend a lot of time talking about the instrument itself. All right, now, what kind of research opportunities are there? Let's talk about that for a minute. These are 7 themes that to me are important in today's technology. The nanoscale origin of macroscopic properties. Those of you that are in mechanical engineering, material science, you're always interested in the macroscopic properties. Well, those macroscopic properties, and depending on what you want, for example, structural materials, turbine engines, any of that, understanding how the structure and the properties of that relate to the nanoscale structure of a material important. The role of individual atoms and dopants, that's good, that's important in semiconductor technology, catalysts, quantum materials, quantum computing nowadays, it's all single atom. Characterization of interfaces at arbitrary orientations, ordered and disordered materials, probing materials in the native environment, okay? The in situ microscopy. Things do not exist always in vacuum. They exist in water, in air, in liquids. We need to understand that. Material far from equilibrium. And then for those, this is something more of an interest to me, conformal mapping of materials in electromagnetic fields. All of these are problems that we need to learn how to address. So there are a lot of scientific opportunities for everybody. And you can look at them, and again, this has to do mainly with what I'm interested in, but some of you will be able to pick out things within this that you'll be interested in, okay? And these opportunities represent technical challenges, not just for the measurement, but also for understanding the problem, okay? And what do we want to do with this? We want to do it quantitatively. We want to do it sometimes at the atomic scale, not always, but a lot. We want to do it in real time, okay? You'll hear that theme coming up. Ideally, in a lot of these, we want to do it in situ. So we want to do it not in vacuum, not in an unknown environment, but we want to put it in a real environment. And what we have to ask here, or the challenge that we're going to try to address in this next couple of days, is how do we use the electron optical beam lines in a way that augments traditional instruments to answer these questions? Okay, let's see. All right, let me give you a few examples of that now before we actually start talking about instrumentation. So high performance materials, defects in interfaces are important. Whether we're looking at dislocations in a high strength metal alloy with precipitation where we're stopping the dislocations, whether we're looking at grain boundaries or interfaces, or are we looking at semiconductor devices where the electrical properties are controlled by what's happening right at the interface. I already gave you this example just in a previous slide, catalysts for performing energy production. Nanomaterials are prevalent in almost everything you do. I'm sure there's a lot of people in the audience, not necessarily here, either here in the room or those of you that are listening remotely, that are interested in nanoparticles. What are the challenges there? Crystallography at the atomic scale, 3D imaging and diffraction, in situ controlled in controlled environments. Again, nanomaterials created. These are the metal oxide framework structures. We see nice little organic cubes that are formed. We see that nice organic cube. The interesting thing is when we look at that in the center of this cube that's grown, we see a framework that consists of platinum, and in the center is nickel. So it's a structure that's being formed electrochemically, okay? But it has unique properties. We didn't know where things were. We're using advanced microscopy techniques today, we can tell that. Okay. Perovskites, I don't know how, if, somebody the other day was asking me, are perovskites interesting? Of course they're interesting, they're engineered materials. This is a layered structure that doesn't exist naturally, it's been man-made. Okay? It's been man-made because in this particular case, it has unique ferroelectric modes. So studying ferroelectricity, for doing phenomenon. And if we look at this, we say, oh, that's an interesting thing, but let's look very closely. What exactly are these phases? What do we see? Well, if we go and look, I'm going to back up a slide for a second. We're going to blow up a region of this. Okay? And I'm going the wrong way. Blow up a region of this, and we can see the atomic layered structure of barium oxide, titanium oxide, barium oxide. At least we think that's what it is. The nice thing that we can do today is the modern analytical instruments can actually measure that. This is a color-coded image, and this is actually an elemental composition distribution. The green is the calcium, the yellow is the titanium, and the red is the barium. And we looked across that very long strip here. We noticed there are changes across there. If I go across it, I can actually map out the elemental changes or distribution across that. And this is a line trace across here. The wiggles that you see are real. Okay? We're seeing the, let's see now, I got to look at the color code here. The titanium distribution, elemental distribution across the planes. The barium, the calcium, you notice the barium and calcium oscillate. The titanium goes through everything. And down across here is the support material that's grown in, the strontium titanate and the strontium titanium ruthenium oxide. So we can characterize all of that and now begin to understand what's going on. Catalysts, materials in real environments. I showed you a brief view before. Here you're looking at nanoparticles in liquid in a TEM. Okay? In the past, nobody would ever have thought of putting liquids in a TEM. You can't do that. Well, we can today. We'll talk about how to do that later. Okay. And for those of you from the biotechnology audience, if there's a few of you out in the audience, studying cancer, nanotechnology has been used quite a bit nowadays in cancer. These are two full-blown cancer cells. They've grown together, and we see structures inside that. You see, this is a pseudo-tomogram. We're tilting the sample back and forth. We can see the structures. With modern analytical techniques, I could tell you that, yes, there's my carbon, oxygen, phosphorus, and the like, but importantly, we see the transition metal components in there, mainly the titanium and the iron and a little bit of the phosphorus. So there's a reaction going in there. Those transition metals in biological systems are extremely important. Okay, soft and hard matter. Again, there may be members of the audience that are working with polymers. Polymers are a challenge, but they're also very useful because we can grow them, they self-assemble, and they can be used in a lot of different processes. So looking at the differences between the structures in polymer fullerene structures and the electrical transport across those, all things that we can do today. Okay, so, this slide appeared a second time. I see I've got it in the wrong spot. This is where it is. So our challenge is this. We talked about that already, so I'm going to skip forward that slide. We've done this one already. All right. Enough of an introduction to give you a flavor of the kind of things we're going to do. So what I'm going to spend some time now is we're going to talk about instrumentation. Because I want you to understand the basic instruments and how they work. Because once we understand the basic instruments, we can take our step forward going forward. So there are basically several kinds of microscopes today. There are microscopes that have lenses. Okay? An optical microscope is the classic example. I'm sure all of you have at some point in your career, whether in grammar school, high school, or as an undergraduate or graduate student, used an optical microscope. Very valuable tool. You can't get rid of them. Then there are the electron microscopes. There are also X-ray microscopes. And there's actually a neutron microscope, but a neutron microscope is designed to look at a railroad train or a truck. So would you call it a microscope? Well, not really. It's not micro, it's macro. Let's call it a macroscope, okay? Then there are microscopes without lenses, Okay? Field ion microscopes have no lenses. Point projection microscopes, scanning probe microscopy, scanning probe microscopes. We're going to deal, oops, sorry, back up. We're going to mainly deal with microscopes with lenses, and I'm going to be focusing in on electron sources or electron microscopes today. And for those of you that came in late, all of the slides that you're going to see over the next few days will be available as a PDF, so you'll be able to take things away with you. Ah, okay, good enough. Okay, so let's back up. So there are two kinds of signals that we look at. We can either look at the reflection or scanning microscopes, and they look mainly at the surfaces, mainly, they do look a little bit, and transmission microscopes, which mainly deal with the internal structure. Modern instruments today can work in both modes, certainly in the TEM environments. We're going to mainly concern ourselves today with simple, with transmission modes. Okay. Now, various beam lines, and we talked about lots of different beam lines. We talked about optical beam lines, X-ray beam lines, neutron beam lines, all have resolution limits and capabilities. So now let's think a bit about what we want to look at. So let's look at different structures and see how big they are. Okay? So what's the classical object that you use to study something? Somebody. What do you call this? Your eyes. What's the resolution limit of your eye? Okay? Okay, good. Let's see if I got the right slide. Yeah, what I call is your personal beam line. You all have your own beam line. Some of us have aberration correctors for our beam lines. I didn't always have this, but after a little while you might need one too. So the typical resolution of your personal beam line is about 1/10 of a millimeter, 100 microns. So what can you see with that? You can see protozoa. Okay? Now, optical instruments give you some magnification. They allow us to see something smaller. Optical instruments take us down to, depending on the wavelength of light that we use, about 1/2 micron. Okay? We can see blood cells, bacteria. It's not good enough to see viruses. Okay? We go to X-ray beam lines, X-ray synchrotron sources. They have probe sizes that can get down to, if you believe everybody, they're just putting in a new beam line at Argonne. The synchrotron at Argonne just shut down last week because they're installing a new beam line. They'll be able to get to maybe 30 nanometers. Okay? But if you really want to go all the way down to the angstrom level, you need an electron beam line. Okay? So the object during the course of the day is to talk about electron microscopy and microanalysis, okay, because we're doing characterization. We're not just doing imaging. So microscopes have traditionally been talked about for imaging and a little bit for diffraction. What I'm also going to be talking about today, which is my personal expertise, is spectroscopy. I use all of these to characterize a material. I'll spend a bunch of time on tomorrow talking more about the spectroscopy part of it, because that augments things. Just to give you a sense of history, electrons have been around for a while, right? J.J. Thomson discovered the electron in 1897. Okay? Through the years, I've highlighted a few things. The first EM was built in 31. Okay? Took about 8 years to get from the first electron beam line to get 10 nanometers resolution. Now, remember, I just told you, just in the previous slide, that the synchrotron at Argonne is about to go to 30 nanometers. Well, we had 30 nanometers back in the 30s. Okay? Now, over the years, we've gone a little bit better. We've gone from 10 to 1. Albert Crew in the late 60s had the first real atomic resolution electron microscope. Okay? 1999, we broke the 1 angstrom barrier. Okay? And in 10 years after that, we broke the 1/2 angstrom barrier. And nowadays, we're doing even more. We're doing high-resolution spectroscopy and imaging. Okay? Now, let's compare, for your benefit, different beamline sources. Let's compare neutrons, X-rays, and electrons, okay? Because you'll have all of those useful in the kind of research you do. What do you want to do with neutrons? First of all, they're all very bright. Electrons are the brightest. Brightness is a measure of number of particles per centimeter per EV. Okay? This is important, the elastic mean free path. How far in a material does a beam have to go before it interacts with matter? So neutrons, as you know, can go through everything. That's why they're used for looking through trucks and car engines and stuff. Have a mean free path of 10 to the 7th nanometers. Okay. X-rays are a lot shorter, 10 to the 3 nanometers. Electrons have a mean free path of 10 nanometers. Okay. What's the absorption path length? And that's how far do you have to go before something starts happening? Neutrons go enormous distances, 10 to the 8th nanometers. X-rays a little further. Electrons are very correct. So electrons are strongly interacting with materials. Okay? And here's the important thing, depending on what's the problem you're trying to solve. How small of a probe can you make? So with neutrons, your probe size is something like 10 to the 6 nanometers. X-rays, maybe 30. And electrons, we can get sub-angstrom nowadays. Okay, the other thing to worry about is the information about the specimen. All information that we get about a specimen has to do with the interaction of our source, whatever it is, and the specimen. And there are two kinds of interactions, okay, two kinds of scattering events. There's an elastic scattering event and an inelastic scattering event. An elastic scattering event means our particle, whatever it is, in the case of electron, EM, it's an electron beam, but X-rays is a photon, neutrons, it's a neutron. An elastic scattering event, the particle interacts and loses almost no energy. It may change direction, but it loses no energy. That's the basis for a lot of imaging work that we do today and a lot of diffraction work. So we'll talk a lot about elastic scattering. Inelastic scattering, the particle loses energy, or it changes direction, or it could be doing both. And again, we'll talk a bit about that because both of those techniques give us information about the solid, and both of those allow us to characterize something very precisely. Okay, so the question that I want you to think about today is, how do we use these scattering processes to characterize modern materials, to characterize the problems that we're interested in? Okay, and what are the limitations of those? We'll talk about both of those. Okay, so what kind of scattering can we see? In elastic scattering, there's a lot of techniques that we're going to be talking about today. We're going to try, and I'll emphasize try, to cover all the things in red. Okay, phase contrast imaging, amplitude diffraction contrast, select various diffractions, high resolution imaging. We'll cover most of those. We're not going to have, certainly not, we probably won't even finish all of these. We're certainly not going to have time to talk about these. We'll talk a bit about scanning transmission. That goes in hand in hand with transmission. We're not going to be talking about SEM. That's a whole nother lecture series. And we're not going to talk about some of the high energy reflection. Oops. So just to remind you, in SEM, we look mainly at surfaces. We can be looking at organic materials, inorganic materials, fabricated devices, and we can get some diffraction effects. In transmission microscopy, we do the same. We can look at organic materials or inorganic materials. So we can look at polymers, nanomaterials, organic structures in diffraction. We can look at grains, grain boundaries, dislocations. We can do high resolution imaging, and we can do advanced diffraction. So we're going to concentrate mainly on this in the next couple of days. Let's give you a couple of examples of that. And again, I will pick from different things. In the life sciences, we can look at cells. So here's a whole cell that we're looking through. We can see the structure of the cell. In a polymer, this is a black copolymer. So there's actually two different polymer species here. I call these the fingerprint patterns. We have one is PMMA and one is PCM. We can look at structures that are grown, nanostructures. We can look at dislocations in materials. How do we analyze all these images? And we can look at very complex things. Okay? Here's a material. It's a man-made engineered material. We go through multiple phases. And the question is, what's going on in each of these phases? Those are the questions we're going to ask ourselves and how to do it. We're going to look at defects in materials and learn how to analyze the defects in materials. This is something that's a very old image. It's part of my PhD thesis back almost 50 years ago. How do you analyze the dislocation structure? We'll talk about that. we'll look at high-resolution imaging. This is a calcium titanate layer, and what we're seeing is this is an atomic resolution imaging. There's a scale bar. Oh, here we go. A scale bar here when we're looking the spacing between individual atoms, and we see changes in that spacing. We also see rotations of the octahedra in there. Okay? All of that has to do with how the material is grown and what its properties are. And then we have what I call nanoparticle soup. Somebody will walk up to you, or you may actually end up with it. You'll come up with something that is, you go, what the heck is this? Okay? We're looking at, can anybody tell me what that is? Well, there's long things and round things, and big things and little things. Your challenge will be to use the resources that are available to you, whether it's an optical microscope, an electron microscope, an X-ray scattering system, to analyze a structure like that. Okay? It's not going to be simple, but you can do it. And we're going to do that using not only elastic scattering spectroscopies, but inelastic scattering spectroscopies. So I mentioned all the stuff we do with elastic. Those were examples of elastic imaging. In inelastic scattering, we have lots of different signals. We can have an incident electron coming in, and we measure an electron coming out. Okay? Those are generally the electron loss spectroscopy techniques. We can have an incident electron coming in and a photon coming out. Those are the X-ray emission spectroscopies. We can have a photon coming in and an electron coming out. Those are the photoelectron processes. And then we can have the X-ray absorption spectroscopy, so photon in and a photon out. So we're not going to talk at all about these. We'll talk a little bit about the X-ray and electron loss spectroscopies. Okay. And what do those spectroscopies look like? They look like an electron microscope with detectors on them. We're going to talk a lot about the two different detectors. You can analyze those. And both of these give us different information about the solid. X-ray spectroscopy tells us one thing. Electron loss spectroscopy tells us something else. Are they complementary? Absolutely. And I hope you're going to see that over the course of a few days. What can we do with some of these analytical spectroscopies? Well, we can look at something like this, a grain boundary in a piece of steel. I can say it's a grain boundary. What's important about this particular grain boundary? It exists. But more importantly, this happened to be a intergranular stress corrosion cracking problem. And an intergranular stress corrosion cracking was happening right at the grain boundaries. And the question is why? Well, we can form an image, and there's nothing really outstanding about that image, right? Well, there's a grain here and a grain here, and there's our grain boundary. What's special about that grain boundary? Why does this grain boundary break and other ones not? That's where we need more than just the elastic image, which is what this is. We're going to go to the inelastic scattering spectroscopies. We're going to go to that grain boundary, blow it up a little bit, and I'm going to take my now electron probe and walk across that grain boundary and measure the composition across that grain boundary. And if we look at this, the composition of the blue, which is the nickel, is uniform. But the composition of the iron and the chromium changes. Why is that grain boundary weaker? We've got a depletion of the iron and an increase of the chromium at that grain boundary. That's why the material fails. Now, different question is, how do we stop that? That's part of your research project, how one determines what's causing it. First, you have to know what the problem is, cracking. Then we have to do a measurement to figure out, is there something significant about that? Yes, we got a change in the composition of the grain boundary. Okay, then the next thing is, how do we answer that question? That's another research project, right? Okay, I'm going to skip that slide. Okay, enough of an introduction. So I've given you an overview of the sort of things that we're going to talk about. Covered a lot of ground, okay? So now we're going to stop talking about global things, feel-good things, motherhood statements about, hey, you can do this, you can do that. You're going to say, well, how do I actually do that? And that's what we're going to spend now. I'm going to spend the rest of the morning talking purely about the instrument, okay? We're not talking about how to analyze data, just talk about the instrument. I want you to understand how an electron microscope works and what's important about it. Because when you sit down in front of that instrument, I want you to be able to say, oh yes, I know what I'm doing right now. I know I have to do X, Y, Z, and this is how I got it. Okay, so the first thing to talk about is some fundamental properties of electrons. Okay. We have an electron, okay? And the electron is, sorry, I'm going to back up a little bit. We're going to have an electron source. It's going to go down through some lenses to hit a sample, and then more lenses to form an image. So we're going to walk our way through the electron microscope now. Okay? So first thing to realize, electrons have certain characteristics. They have certain energies, and they have a certain characteristic wavelength, okay, lambda. Okay? That wavelength is determined by the accelerating voltage of the microscope. And you should always remember that when we talk about the accelerating voltage of the microscope, everybody says, I have a microscope that runs at 30 kV or 60 kV or 100 kV or 200 kV or 300 kV. That's just the accelerating voltage. That's not necessarily the energy of the electron beam. Okay? Because when we start going from something relatively low in energy, 10, 20, 30 kV, those are relatively low energy electrons. As we start going up to 100, 200, 300, or even 1,000,000 volts, now we're starting to get to electrons that are relativistic. So they're relativistic corrections that you have to do always. Okay? Just to give you a sense of that, as a function of accelerating voltage, this is the wavelength of the electron as a function of accelerating voltage. And I've highlighted some key areas here because, let's see now, you've got a 300 kV Titan here, right? Okay. So the characteristic wavelength that we have for your electron beam here, you look at the wavelength here in terms of angstroms. It's well sub-angstrom, okay? That doesn't mean this is the resolution you get, but this is an important parameter to know. So knowing the wavelength of the electron for your different energy instrument operations is important. Okay, so all microscopes use lenses, and all microscopes have the same characteristics. They have an illumination source. In this case, if you're an optical microscope, it's light. We have lenses that bring the illumination to the specimen. Then we have magnifying lenses, and then we have some kind of detector. Okay? So we're going to work our way through that. Okay? So that was an optical microscope. This is what a transmission microscope looks like. So sorry, I've now flipped things upside down for you. So we've got a source, okay? We've got accelerator to bring that electron beam to a certain energy. It's focused by lenses to a specimen. Electrons or light or whatever is scattered from the specimen, goes through additional lenses, and goes to some sort of detector. This is a real electron microscope cut in half. It's a bit of an old one. It's an old RCA EMU3, and we physically cut it in half. It actually took 3 microscopes to be cut in half to make this. It's difficult to do, but I want you to get a sense of what's going through it. And we're going to look at the individual components. So we have an electron gun. So at some points at the very top, so let me back up. So I'm going to show you pictures of different sections here. So we have the electron gun. So we got a high voltage cable in that brings our high voltage in to a very small filament that's heated, and that's our electron source, and the electrons go out. They come down the column through various lenses. We'll talk about lenses in a moment. What you have is pole pieces surrounded by copper wire. We run current through the wire to create an electromagnetic field, which focuses our beam down through the column, eventually hits some sort of detector. This is a very old microscope. You can see it's been around for a long time. It had a fluorescent screen. That's back when we used to look at fluorescent screens, or when I used to look at fluorescent screens. And the detector then was a fluorescent screen in your eyeball looking at it, and when we wanted to record something, we put a sheet of film down underneath and lifted up the screen. I don't think your machine has film in it anymore, does it? No. You still have a camera, though? Yeah. Okay. Okay, what about the electron sources? What kind of electron sources are there? There's actually 3 types. There's a piece of tungsten wire called a tungsten hairpin. Okay? It's literally a piece of wire, very thin. We heat it up. We run current through it. It heats up, glows red hot, and the glowing process, it's emitting light, but it's also releasing electrons. Okay? There's the lanthanum hexaboride type filaments. That's also a slightly heated filament, but it's also a partial field emitter. We'll talk about that for a minute. Electrons come off from the tip, and then there's the field emission sources that you'll have in your machine downstairs. Do you have an X-FEG or a cold FEG? X-FEG, okay. Okay, thermionic sources are fairly simple. It's a piece of wire that we heat up to a certain temperature, and we get current that comes off of it. Okay? The amount of current that we get is proportional to the temperature. So you want more current, what do? You turn up the wick. The problem is when you turn the wick up too much, what happens? You melt the wire. So typical failure of a tungsten filament is you've melted it. Okay, you've heated it up too long. Eventually, however, remember, even if you don't overheat it, but you're just heating it up and leaving it, slowly the metal is coming off. Okay, you're slowly evaporating the tungsten, and these filaments always fail. Okay, they will always fail, and there will always be a break. Okay, is that good? Yeah, no, we don't really want it failing because that means we've got to stop and change the filament. How long they last? It depends on how well you use the instrument. Do you have any tungsten filament machines here? You do. SEMs mainly.
I mean, when the lab 6 goes, then we use tungsten filament.
You use tungsten, okay. Tungsten's fairly cheap in dollars. For US dollars, I don't know what it would be in Indian rupees, right? But dollars, $20 a filament, roughly on that order, okay? 2,000 rupees, is that right? No. $20 would be 20,000 rupees, okay. Relatively inexpensive in that thing. The other type of filament, and there's different types. There's the bent hairpin, sharp ones. LAB6 is another filament. It's lanthanum hexaboride. It's a crystal that is a partial field emitter. If we heat them up a little bit, they give off even more electrons. They're very nice, very coherent sources. They're also very expensive. If this guy is $20, this guy's $1,000. Okay? So you want to be more careful with these guys. And as we've just heard, if the LAB6 goes out, you replace it with a tungsten until you get another LAB6. Okay? The third type is the field emission source. Okay? The field emission source is literally a single crystal, usually of tungsten, sharpened to a very sharp point. Very rare. They are sometimes slightly heated. There's both cold field emission and heated field emission. They rely on electron emission just by putting a large potential between the tip and an anode, and we get a field emission source coming out. Electrons are literally ripped out of solid. Okay? They're very nice. They're very small probes. They're very expensive systems. Okay? Replacing a field emission tip is an expensive process. You don't want to burn them out too often. But they do last. I've had a field emission tip running for 3 years. Now, I'm pretty careful with it. And I'm sure that the field emission tip in your Titan machine here is well taken care of. There are some problems with the different, characteristics of tips. As I mentioned, thermionic tips are cheap, they're inexpensive. They're relatively low brightness, okay? LAB6 are brighter beams with more visibility. Field emission are the brightest, okay? On the flip side, go over to this end, thermionic tips can work in relatively poor vacuum. LAB6 needs better vacuum. Field emission needs really high vacuum, okay? So this is part of where the cost is, right? These are cheap and inexpensive. They work in lousy vacuum. They can take a beating, and they're not too bad. As we go better, hello, sorry, I didn't want to do that. As we go to a brighter source, which means a smaller probe, the requirements on the vacuum get better and better. So these field emission guns are not typical machines that you use routinely unless you take care of them. Okay? The other characteristic about the different sources is the amount of current in the probe. So this is a function, this is probe size versus current. So the very large probes, the tungsten and the LAB6 have a lot of current and they're very big probes. The field emission guns peter out. As the probe size starts to get smaller, so for smaller and smaller probes, the amount of current decreases dramatically. So when we want really small probes, we tend to go to a field emission gun. So we have lots of current in small probes. Okay, how are we doing? 10:30. When did you want to take a break?
Another 15 minutes.
15 minutes. Okay, good. Okay, so we've talked about the electron sources. Let's talk about lenses now. Why do we need a lens? Okay. There are a lot of lenses in an electron microscope. So far, we've been just talking about the electron source, which is up here. Okay? There are a whole slew of lenses. We'll talk about the different lenses in a few minutes as we go through it. Skip this slide. Okay, so the TEM column, which is mainly what we're going to be talking about here, consists of an illumination system. We've already talked about the source. We have an illumination system, an image forming system, and then a projection system. So this makes the probe. We bring the probe to the sample. We magnify the image from the sample a little bit, the first image, and then the projector system gives us even bigger magnification or different operating modes. And that all goes down to a screen where we detect things. Okay, the illumination system, the role of the illumination system is to bring the probe, the electron source, to the specimen. Okay? And there are a lot of different ways of looking at it. We'll get back to this slide in a little bit later. Okay? It's actually in the wrong spot. Okay? Actually, this is in the wrong spot too. Okay, let me just see. Let me move forward here. Okay, yes, this is the slide I wanted. Sorry, those two slides were out of order. That's what happens when I put things together late at night. All right, so why do we need a lens? Okay, let's ask ourselves. We have a beam of electrons, right? The problem is we have our electron source, and we've turned it on. I don't care what kind of electron source, any electron source. The electrons are emitted from the tip, and they go off in all directions. So what we want to do is we want to bring those electrons, rather than scanning them in a large area, down to a small area. And that's the role of the lens. Okay? Lenses have a lot of functions. One of them is to take a source and bring it down focused to a point or to an image. Okay? In electron microscopy, we tend to use something called an electromagnetic lens. Why? Because that's the easiest type of lens to build. Okay? There are also electrostatic lenses. We won't be talking about those today. How does a lens work? It's very simple. Most of you have already had your basic physics courses. You know something called the Lorentz force, right? So what happens if you have an area of a material which has either an electric field or a magnetic field in it, and we have a charged particle going through that? The Lorentz force, whether it's an electrostatic Lorentz force, the force is equal to charge times the electromagnetic field. If it's an electromagnetic lens, it's the velocity of the charge times the velocity of the particle crossed with the magnetic field. Basically, what's happening is you have a charged particle going through a region of space where there's a field, either electric or magnetic, and that causes the beam to deflect. Okay? The nature of how that deflection goes is proportional to the size of the electrostatic field or the magnitude of the magnetic field. And that only exists over the region of space that the field is extending. So once we get out of the region where the field is, the particle keeps traveling in a straight line. Okay. Lenses in an electron microscope are formed by coils of wire. Okay, we have loops of wire. You've all made electromagnets, I'm sure, at some point in your time. Taken a wire, wrapped it around something, put voltage across it, and you made a magnet. You've made a lens when you've done that. Okay? In the case of an electron microscope, we have lots and lots of windings going around. So you can see the windings here. The windings are so finely spaced here you can't actually see the individual wires. Okay? We run a current through that, which creates a magnetic field in this direction. Okay? You also know that if you put a piece of metal inside a winding, you can intensify that magnetic field. So all microscope lenses have a pole piece, which is a piece of metal. Usually it's an iron cobalt alloy to increase the flux and concentrate the flux in a small area. Okay, there are lots of different types of lenses. There are condenser lenses, objective lenses, and there are different types. We have a symmetric lens where these are the windings, and these are the pole pieces with a small hole down the middle that the electron beam comes down. We can have snorkel lenses, and we have quadrupole lenses. Okay. What's important about the lens, just to give you a sense of it, is that right in the middle of the lens, there's no focusing action, okay? All of the key parts of a lens happen right at the very tip of the pole pieces. Why is that? If it's an electromagnetic lens, you have a particle going in one direction, forward. You have a Lorentz force. What is the Lorentz force? It's when the velocity of the particle is perpendicular to the magnetic field, okay? At this part of the lens, the magnetic field is parallel to the velocity of the electron. There's no focusing action done here. All the focusing action is done right at the tip of the pole piece where the lens, the magnetic field is actually bending slightly, okay? That's where your Lorentz force is. Why do I make a point about that? Because at some point in your life, you will be interacting with your microscope. You will have a pole piece. What you don't want to happen is you don't want anything to happen to this area. If you have think of it, your sample is going to be sitting in between the pole pieces. The key area is right here, right at the pole piece, right at the entrance. I don't care what happens here. I don't want you to affect this shape right here. I don't want you to chip it, to bend it, to do anything to distort this, because that's where the key features of the magnetic field are. So you always most microscopes actually have safeties. They have safeties so when you get close to hitting a pole piece, it'll stop you from doing it. You can always defeat safeties. That's unfortunate. So this is the key area that you always have to protect on a microscope. Okay, we've already seen these images before. Let's skip forward. How do we get magnification with lenses? Okay. Magnification is quite simple. We have an object. We do a simple, sorry, I keep doing that. I didn't realize this was a touch screen. We have an object. The rays come past the object through a lens and focus to a point. The magnification is simply the ratio of the distances of the object space to the image space. So magnification is just B over H in this case. The closer, the difference in the ratio between A and B is what gives you your magnification. All right, so if we have one lens, we have one magnification. All microscopes have multiple lenses. Why? Because we need to get higher and higher magnification. What do? We magnify the first time, magnify the second, magnify the third. So we stack lenses one on top of each other to get increased magnification. By controlling the strength of the lens, we control the focal length, which is control the distance between A and B, and control the magnification. So when you're changing magnification in a microscope, what are you doing? You're changing the amount of current in different lenses, and that's giving you different focal lengths and hence giving you different magnifications. Most transmission microscopes today have an objective lens, which runs at constant power. Usually don't change that one at all. But you have several post-specimen, post-objective lens lenses, and that gives you your magnification. All right, so we've magnified something. The important thing to do when you magnify an image in your electron microscope is to know, what's my magnification? Very important. Whatever you do, you will see a knob on your microscope and it'll say magnification 10,000x, 20,000x, 100,000x, 1,000,000x. That's fine. It's an order of magnitude. Don't trust it. Okay? What I want you to do is learn how to calibrate your microscope for your conditions. Okay? And what you will do is you will have some sort of standard specimen with known spacings, okay, one of which you can buy. It's called a replica. It's a diffraction grating. We know exactly, in this case, 2160 lines per millimeter. We can put this in the microscope. We take an image at whatever magnification is. We measure that distance. We know what it is, okay? And you can then calibrate the magnification. The number on the microscope will never be correct. It will always be wrong. It'll be close. Manufacturers go to great efforts to make it approximately right. You go to 10,000x and you say, yeah, that's about 10,000x. Okay. But if you need to do an accurate measurement of anything that you're doing, I want you to go in, make sure you've done the calibration. Okay? Make sure you know it. And just because you've done the calibration, there's certain key things in it. Your specimen height has to be right. Everything has to be right. You'll learn that when you do your training of the microscope. You should do a calibration for yourself, store it, and keep it with your records. Okay, that's good for low resolution, for relatively low resolution, up to 50, 60,000 times, something in that range. But once we start getting to very high resolution, what you're going to need is another calibration. Okay? When you're up at 1,000,000x, what do you use as a calibration? Those lines at 2160 lines per millimeter are miles apart. We'll never see them. So what we do is we prepare internal standards. Use a pure element. The typical thing that's used nowadays is silicon. You can get pure silicon. We can make silicon samples. We know the crystal structure of silicon. We know the lattice spacing of different atomic planes of silicon. What you're looking at here is a single crystal of silicon. These are atomic columns. We know the spacing of these planes, and so I can use that for high resolution calibration. Again, learn how to make you need the sample. Can you buy this? Yeah, you can buy silicon specimens if you can't make one here. But learn how to put it in, get a microscope, get an image, and do a calibration. The other thing we do quite often is you move the beam around. Okay? There's something called beam control, beam deflectors. Okay? How do beam deflectors work? Well, you already know how they work. They use the Lorentz force. What they are coils, okay? Either above and below the objective lens. They're the same coils that you have here, except turned 90 degrees. They create a magnetic field going back and forth. And what does that do? It simply deflects your beam back and forth. So it's the same as doing this, but except we're not really doing too much focusing because the field extends very small. So all it does, the beam comes in and deflects. Okay? So you have deflectors. These deflection coils exist in many places. They also do several functions. One can be just a simple tilt of the beam. We can bring the beam in. We use two coils to do a beam tilt. One beam comes in, tilts it a little bit. Second beam tilts it even more. Okay? We can also we do multiple tilting, or we can do just a simple deflection. And to do a simple deflection, what we do is we still need two coils. We deflect once and then deflect back. So these coils are working opposite directions. Okay. Astigmatism is a problem in everything, not only for people with bad eyes. We can never make a perfect lens. There is no such thing. Okay? All lenses, even if we machine it as accurate as we can, will always be slightly asymmetric. What does that mean? Because it's slightly asymmetric, we will have electrons that are focused to different points depending on where they're coming through the lens. So what you will have is a disk of confusion. So in order to fix that, we use something called a stigmator. And a stigmator is a set of coils similar to deflection coils that are surrounding the sample. And what they do, they cover a very large area. And what we can do is compress or expand the beam. Okay? We can have lots of different kinds of stigmators. We can have 4, even 8 to surround the sample. Okay? How do you know you have an astigmatic beam? Well, just look at it. This is a beam, a focused beam, which is astigmatic, right? It's not round. It should be round. What we do is we use the deflection coils using the stigmators. We're squeezing and expanding the beam to make it round. Okay? That's what a stigmator does. And all just a simple set of coils. Okay? How about astigmatism in our image? Okay? Again, we've got a lens. We formed the probe. We made a nice round probe. Now we hit the sample. Now there's other lenses past the sample. You will see astigmatism in your image. And how can you recognize it? There's a lot of ways to recognize it. The simplest way is when you look at a focused image, and we'll tell you what a focused image is in a minute, and we look around the edge of the image, you will either see a dark line or a bright line. Okay? And you look at this one in particular, you notice it's asymmetric. Here it's really black and dark, and all of a sudden it changes white. Okay? The effect that we see here is called a Fresnel fringe. We'll talk about that later when we talk about imaging, but the fact that it's not symmetric, going all the way around, tells you you've got astigmatism. What your stigmator will do, just like the probe stigmator, now we have an image stigmator, a set of coils. What we can do is adjust that stigmator, and you notice I've adjusted the astigmatism here, which is asymmetric, to be perfectly symmetric. Okay? Learn how to do that. This is generally done at low magnification. at very high magnification, we're looking at an image, and how can you tell if we're astigmatic here? You really can't. If your eyes are trained and you learned how to do it, you can look at the image and say, yeah, that's definitely astigmatic, because what I do is I'll look at this and I see a little bit of streaking this way. And what I want to do is I don't want any of the streaking. This is the same area that's astigmatic, and this is corrected. Okay? Now, I can look at that and tell the difference. Nowadays, there's an easier method, rather than straining your eyeballs, and that's by taking a Fourier transform of that structure. If I do a Fourier transform of an image that's astigmatic, I will get a set of concentric rings that are elliptical. I can then use my stigmators to make those ellipses round. Okay, so I've gone from an astigmatic image to stigmated images. This method only works at high magnification. At lower magnification, you use the other method. Okay? The other thing Fourier transforms are also very good with is they're very good for showing you problems in the instrument. We'll look at this image, and you say, is this astigmatism? Is she streaks? Okay, well, what was happening is the sample's moving. Okay, so we're seeing streaks here. When I look at a Fourier transform of something that's moving, I see bars perpendicular to the motion direction. Okay, so we can see those large bars. When the motion is minimal, it's just round again. Okay. You can also look for problems. If you have a turbo pump on your system, I know you do. Turbo pumps, vibrations in the room, noise in the room causes vibrations. This is a turbo pump motion. You'll notice there's a cutoff here in the Fourier transform. That's due to the turbo pumps vibrating. When we cut it down from full speed down to slower speed where it's not vibrating, that goes away. Cell phones. This is an image in our atomic resolution microscope. Cell phone was off, cell phone was on. And nobody was talking. The cell phone was just on. So there was an electromagnetic, the communication from the cell phone tower was penetrating the microscope room, causing electrical interference in our power supplies. So don't have your cell phone on when you're working in the microscope room. Okay, I think this is a good time to take a break. Let's take what we used to call them bio breaks in the States, and then we'll continue with apertures versus lenses. Okay, good. So we'll pick up here, and how long do you want to take a break for?
20 minutes.
It's up to you. You pick it.
20 minutes.
20 minutes. All right, we'll just meet back here. troops. Let's do that. All right, gang, let's move back in.
I remember we used to take your service in Pico. Yes.
Yeah, no, if I do with this microphone on, I have a very loud whistle. Yes. I could probably whistle from here with the door shut and they'll hear me. Testing, 1, 2, 3, testing. How's the audio now? I'm going to turn my head back and forth. Can you hear me okay both times? Okay. Good. So we got the audio fixed. That's good. All right. Any burning questions from so far today? Have I put you all to sleep? No? Okay. Just remember, the important point is if you get a question, ask the question. Okay? Because I'm going through stuff at double the rate I normally do because there's a lot of material to cover. And I'm trying to get through it, and I probably should have thrown half of this out. Are we set? All right, everybody, if you want to get a copy of the PDFs, send an email to Barun. He's in charge, right? Where are you? There he is. All right, so we spent a lot of time talking a bit about source. Well, we talked a little bit about microscopy, we talked a little bit about sources, a little bit about lenses. Now there's other things I want to talk about in terms of the instrument, and we're going to carry on with that, okay? Next thing I want to talk about is we had a lens, we have a beam. We had that beam come down, go through some lenses, and come down somewhere else. All right, but that beam is never perfect, okay? And you all know, and for those of you that do photography, you know you have apertures in your cameras. Well, we have apertures in the microscope too. We're going to talk a little bit about the role of the apertures because it's important to understand how the apertures affect things. So, first of all, and by the way, I tried to use for those of you listening remotely, I tried to use the laser pointer function on my laptop, but then it stops the advance, so I'm not going to bother. So we talked about how lenses take the beam and bring it down. What we haven't talked about is the fact that in addition to lenses, we also have apertures in the column. And the apertures provide several functions. First of all, they get rid of very high angle scattered electrons. Even though we have a lens, we don't focus everything down. So some of these electrons come off at wide angles. We really don't want that coming down the column. So the role of apertures is to restrict the beam. It also, because the apertures cut off some of the beam, control the beam current. Okay? There's another thing that the lenses do is, in addition to controlling the amount of current and the size of it, they control the size of the probe. So we're going to look at both of those in a moment. So first of all, we can put back up. When we put an aperture in, there's several things that happen. First of all, when we put an aperture in, it restricts the size of the probe. So I'm going to show you that next. Let's see. So here's a large aperture, 70 microns, relatively large. And here's a small aperture, 30 microns. What's happened? The probe, the size of the probe has gotten smaller. Also, very importantly, is this happens to be a field emission gun instrument. And if you look very closely at the image of the probe, there's no sample in the way here. This is just the beam going through vacuum. We see fringes, okay? Okay, those fringes are Fresnel fringes. We'll talk about Fresnel fringes a little bit later. But it's very important to realize that as the probe gets smaller, and as the area from which you take the electrons from the source to a smaller and smaller area, the probe gets more coherent. Okay? So in addition to being Fresnel fringes, these are also a measure of how coherent the beam is. The more coherent the beam is, the higher resolution image you will get in your TEM image. Okay, so we can go from a large probe with a lot of current to a smaller probe. We can also go from a less coherent probe to a more coherent probe. Okay. We can also use the lenses. I'm going to back up again. We can also use the lenses to make a small probe and a large probe. This is something called a strong cross lens and a weak lens. Okay? That's in the microscope terminology, that's usually called the spot size of the microscope. Okay? So here I compared the same spot size 3, it's a setting on your microscope. What does it mean? It's the third setting. There's nothing magic about the 3. You have 1 through n. On my microscope, my spot sizes go from 1 through 17. Different instrument manufacturers have different nomenclatures, but this is spot size 3, which is, to me, the smaller the number, the bigger the probe. Why they use that notation, I don't know. It's backwards, but that's what they did. Okay? So now I'm going to go the same size aperture, 30 micron aperture. I'm going to go from a large beam, spot size 3, to a much smaller beam, spot size 9. I'll keep the probe size the same thing. But you notice the number of coherent fringes has increased. Okay? So the beam is more coherent here. But look at that beam really close. There's a lot of noise in here. There's less noise in here. Why? Because there's less current in the probe here. Okay? So it's a more coherent probe. How do I know that? There's more fringes. You can see those fringes go right the way to the middle now. And here they sort of peter out or die out. Okay? No. So a more coherent probe, better resolution in many cases, but less current. Okay. The other thing that the probe does is the condenser lens does, it controls the size of the probe. And the way you do that is by controlling the strength of the lens. Okay? Now, there's one thing to remember about focusing your probe down, and that has to be, are we on an over-focus condition, an in-focus condition, or an under-focus condition? So let's take focus first. When I say the probe is focused on the sample, that means the beams converge. Forgetting about aberrations, they focus right on the sample. If the probe is over-focused, okay, the lens is really strong because it's focusing shorter. So that's an over-focus condition. So the current is greater than what you need to reach focus. And if we're under-focused, the lens is weaker. Okay? Now, that also has an effect on something called the convergence angle. Okay? So in this case, we have a smaller angle when we're in the under-focus condition than in this case. We have a larger angle. That's also important when we talk about imaging, when we talk about under-focus and over-focus. Okay? Generally, we tend to run either at focus or under focus. Can you work over focus? Yes. But notice the beam convergence angle, and that'll be important later, is bigger than in the under focus. So this is a focus probe, this is a under focus probe, and think about it. If I want a parallel beam, what do I have to do? I weaken the lens. So I go to an under focus condition, so probe size decreases. What's going to happen when I weaken the lens? This beam is going to spread out further and it's going to go to a more parallel condition. So the other thing in most microscopes, and this is just a rule of thumb, there's always a knob that you turn to change the lenses. Nowadays, in the past, that used to be a real knob that turned a resistor and that made something happen. The convention has always been when you turn the knob clockwise, you're increasing the current. When you turn it counterclockwise, you're decreasing the current. Okay, that's usually the convention. Okay, particularly on the older microscopes. The newer microscopes, because there's so many lenses, it's hard to keep track. But generally, when you say I want to go to unfocus, you generally go counterclockwise. That's weakening a lens. And generally, when you go clockwise, you're strengthening a lens. Okay? Just keep that in the back of your mind. Now, there are a lot of different kinds of microscopes. We're going to be talking later. I think we talk about TEM imaging tomorrow. Yeah. We're going to be talking about TEM and STEM. There's really no difference between the two. Okay? In TEM, we have a beam hitting the sample. In STEM, we have a beam hitting the sample. Okay? The real difference between the two is that in STEM, we almost always have a focused probe. In TEM, you can have the same focused probe in TEM as you can in STEM, but in TEM, we tend to have a more parallel beam. Okay? In STEM, we tend to have a more focused beam. The other reason it's called scanning, STEM, is because just like in a scanning electron microscope, where we can move the beam back and forth across the sample, you do that in STEM. So that's why it's called scanning. Okay? And that has a lot of advantages for doing some work. Okay, so in STEM, the important difference is we scan the beam back and forth. And remember I told you about deflection coils, that we had deflection coils. And the way the beam scans across the sample is very important. Remember I told you we have double deflection systems, which do two things. They can either tilt the beam or they can deflect the beam. And all STEM systems today have double deflection coils. And what that does is we can take a focused probe and move it parallel across the surface of the sample. Okay? In addition, in addition to having a convergent beam on sample, we have detectors underneath, and we'll talk about that a little bit later. But in STEM, we have multiple detectors underneath. Mainly in transmission microscopy, we have one detector underneath. Usually, it used to be a piece of film. Nowadays, it's either a video camera or a CCD or some sort of electron detector. In STEM, we have multiple detectors down, and we'll talk about how the different signals come about and the information in the different signals that we can get from STEM that we can get in TEM, but it's more difficult. And why do I bring that up? Because the nice thing in STEM is that we can focus the probe down and stop it on, and not only get very high resolution images because we have a very small probe, we can stop probes in different spots and measure spectra, and we'll talk about this in terms of spectroscopy later. Okay. So far we talked about getting the probe onto the sample, hitting the sample, and then scattering. Okay. There are more lenses. We talked about mainly up to this point we talked about just bringing the probe down to the sample. There are also lenses after the sample. Okay. And in those lenses allow us to go between different operating modes of the microscope. Remember, I told you it's a microscope. Well, I called it an electro-optical beam line. Well, most people call it a microscope, and most people think of microscopes as just doing an imaging device. The important thing that we're going to talk about, is it this afternoon? This afternoon is diffraction work. So we want to be able to change the operating mode of our microscope between looking at an image and looking at something called a diffraction pattern. We'll talk about what diffraction is this afternoon, the basics of it. But the way we go between different modes is our objective lens, our main imaging lens, always stays the same. It either forms an image, so our sample comes here. There's a lens after it that transmits the beam that hits the sample and takes the image from the sample and transfers it to a certain plane. That's the focal length of the lens. Okay? We can look at either the image plane, or we can go backwards and look at a plane that's right here where all the crossovers are. And this plane is the diffraction pattern. Okay? And the way we get either an image or a diffraction pattern is using the lenses after the microscope, and we adjust the lenses to either look at the image plane, or we change the strength of the lens to look at the back focal plane, this plane. Okay? And in one case we get an image, in another case we get a diffraction pattern. Okay, let's see now. So, we looked at an image similar to this before. In fact, it's the same area. And the question is, how do I know when my image is in focus? How do you know it's in focus? You know it's in focus when every electron scattered from the sample goes down to the screen. Okay? Now, how do I know every electron has gone down to the screen? What I look for in an image is the absence of a Fresnel fringe or minimum contrast. What's minimum contrast? Minimum contrast, think about it. If a beam's coming down through the sample and it scatters, and we take all the electrons that have scattered from the sample and bring it down to whatever our detector is, we've collected every electron. We've focused the image. Okay? Now, when an image is out of focus, we get more contrast. Why do we get more contrast? Because we've thrown away some signal. Okay. The Fresnel fringes that we saw, you see when your image is out of focus. Okay. We get either a black fringe or a white fringe, depending whether you're under focus or over focus. When you're at perfect focus, all the Fresnel fringes almost completely disappear, or the contrast is minimized. So the easiest way to focus your image, go to minimum contrast. Now you're in focus. Okay? Now, I mentioned the Fresnel fringes. Where do Fresnel fringes come from? Fresnel fringes are literally a diffraction effect. They come whenever you have a beam hitting the edge of something. Okay? Now, when we looked at the apertures, I showed you apertures and we looked at the beam, there was always a Fresnel fringe there. Okay? That Fresnel fringe came from the edge of the aperture that you're using to form the probe. When we looked at a sample, there's an edge on the sample. We're getting a diffraction effect from the edge of the sample. So we can get Fresnel fringes from a lot of different things. We can get them from the apertures, which forms here, or we can get them from the sample. I think that's the next slide. Yes. Yes. So there's the Fresnel fringe because we have an edge on the sample. Now, here I've adjusted the astigmatism so that my fringe contrast is uniform, right? It's the same width all the way around, okay? Whether it's a black fringe or a white fringe, okay? And I use a simple mnemonic to remember things. Black is over focus, white is under focus. And to me, it's alphabetical. B and O are closer together than W and U. So white is under, black is over. So that's my simple way of remembering, because I always mess it up, to be honest, okay? And perfect focus, again, is when there is no fringe, we're at focus. So that was the previous, was that the previous image? Let me back up. That one is perfect focus. Okay. Always important to understand when you're taking your image, are you over focus or under focus? Now, I will tell you ahead of time, oops, wrong way. Everybody, almost everybody, likes the over focus image. And they like it because it's easy to see. That's the wrong focus plane to use. You should always be either at focus or under focus, okay? Okay. This is easier to see. Your eye likes it. Your eye likes contrast. Your mind likes contrast. But that's a bad mode to generally run in. You generally want to be either under focus or at focus. And most times it's slightly under focus is always better, okay? Now, I'm going to ask a question. Here are two high-resolution images, and the question is, which one of those is in focus? So you're going to run into this, particularly if you start using the atomic resolution microscope that you have here in Madras, okay? You're going to get high-resolution images, and you're going to want to know, I got this beautiful high-resolution image. Am I in focus? How do you tell, okay? Here are two images, and I look at both of these, and I say, oh, I like this one. Why do you like this one? Because there's contrast in that one. That's an out-of-focus image. That's when the contrast is minimized. That's the in-focus image. There's another way of doing this, and when we, on the microscope system here, you have a digital camera. Which camera do you have? Which one? OneView, K2, K3, any high-resolution image?
I think it's K3.
K3, okay. Well, in the new digital imaging systems, you have a digital image now, no longer film. I used to do it this way, because that's the only way to do it. In the new cameras, we have a digital image. Because it's a digital image, I can take a Fourier transform of the image and get a Fourier transform of that structure. Here's a Fourier transform of that structure. When I'm out of focus at high resolution, what I will see are concentric rings. Remember, these concentric rings we used before to adjust astigmatism. Well, they also tell you you're out of focus. As we go closer to focus, these rings start to expand, okay? So we're going from out of focus, closer to focus, more closer to focus, and now you can almost not see the ring at all. Okay? Okay, and if you continue, the rings will start collapsing again. So you'll actually see the rings appear and decrease. So you go through it. And at focus, which is that image, I should have reversed the two. And when you're at focus, you don't see the rings, and it'll be a washed out Fourier transform. Okay, so we said let's focus the image. And the question is, what limits our ability to get a perfect focus? And we already said that a little bit ago. It's because we can't build a perfect lens. Let's see, can we go forward? Yes. We can never build a perfect lens. Even with the aberration, with the stigmators to correct astigmatism, we can never get it perfect. And the reason for that is no lens is perfect, even with the stigmators. There are two aberrations that always exist in a round lens. What's a round lens? The kind of lens that we've been talking about. It's spherical. Okay? There are two lenses. One is called spherical aberration. The other is called chromatic aberration. Okay? And the reason that we have these aberrations is I told you about the focusing action of the lens, and I told you that at the entrance of the pole piece, the magnetic field is changing, and that's where all the focusing happens. Well, at that point, the magnetic field is not uniform. It's actually, as you go away from the center of the lens, the magnetic field actually gets a little bit stronger. And what happens when the magnetic field gets a little bit stronger? The electrons bend a little bit more. Okay? When they're coming straight through, they get focused to a certain point. When they go a little bit further out, they get focused a little more. So what happens is we get a range of focuses. That's called the spherical aberration of the lens, and that's proportional to what? The strength of the lens, and also to the angle at which those electrons are scattered through. So it's proportional to some constant, the spherical aberration coefficient of the lens, times the angle at which we're measuring. How can we reduce that? Well, if we put in a smaller aperture, what's it going to do? It's going to reduce that angle, and so it'll reduce the aberration, so the focus point will get better. Okay? That's one aberration, spherical aberration. The other aberration is called chromatic aberration. Now let's pretend, forget about this for a moment. Let's say we had a uniform beam coming in. Electrons of one energy will get focused to one point. Electrons of a different energy, i.e. different velocity, will get focused to a different point. Oh, but you have a 100 keV electron beam and you just told us how nicely focused it is. Well, that electron beam has a source and it has an energy spread. That energy spread can be relatively small. It's only about, depending on the source, for a thermionic gun, it can be about 3 electron volts. For a field emission gun, it can be 1/4 of an electron volt. But it's still an energy spread. And that energy spread causes the beam to go in and out of focus of a plane. So we have two aberrations, spherical aberrations and chromatic aberrations. How do we cure this one? Well, we have to change the focus of this. How do we cure this one? We have to make the beam monochromatic. Both of those are difficult. Okay? Mechanically, trying to make a single perfect lens is a fool's journey. Don't try it. Not going to happen. Been tried for years and that never happened. And it's a fundamental limitation of all lenses that you have this aberration. Okay, so there are other ways of getting around it. And we'll get to that in a minute. Okay, so overall, when we look at aberrations of a lens, aberrations are related to the convergence angle that we just talked about, right? The angles of the beam. Notice the angle either coming in or it's related to the angle back here. So we got two angles. Okay, so we can write the probe size, probe diameter, as a function of convergence angle. It's going to, as the convergence angle gets larger, the probe size changes. When it gets too large, it starts getting worse. Okay, so we have a diffraction limit and we have an aberration limit. Okay, this is your spherical aberration. This is your basic diffraction limit. So we have multiple things. The probe size is the image, the diameter of the probes added in quadrature. So you've got the spherical, the Gaussian, and the diffraction limit. I haven't shown you the chromatic aberration effect on this one yet. Okay? So there's an optimum range, and there's an optimum for each angle. There's an optimum resolution that you can get. I'm going to show you the effect of aberrations of those angles. Okay? So first, we're going to look at, can we see the aberration? So I'm going to go back here. Can we see these aberrations affecting the probe? Okay? So remember I told you the larger the probe, the larger the angle, the bigger the aberrations. So this is a very large aperture, 150 microns. That means it's a very large angle. We have a focused probe, but look very closely here. Those of you that are looking on the screen can see this. You can see a tail that's coming out. That's the aberrations of the probe. Okay? So it's a very bright focus point, but there are aberrations. There's tail of electrons. If I go from 150 micron to a 70, what am I doing? I'm cutting that out. Boom. I'm going to make that smaller. The aberrations got smaller. Go to a 30 micron, it gets even smaller yet. Okay, so you can physically see aberrations if you look hard enough. The other thing to look at is making sure you have a good aperture. This is a nice, clean aperture. It's relatively good. This is a dirty aperture. Okay, bits of junk coming on. Okay, pieces of dirt that's fallen on the aperture. Here's a really bad one. Okay, so how can you tell if your aperture's dirty? Just look at the probe. Okay, if you see things like this, you know you have a dirty aperture. Question, is that important? Well, if I'm only interested in this area, is that affecting me? No. But if I'm trying to focus that beam down really small, these guys are going to get in the way. And now let's just skip that. We can just measure it. Okay, that was aberrations in the probe forming system. We have similar aberrations in the image forming system. The same thing. Remember, we've got the angles coming in and the scattered electrons going through lenses. We have post-specimen aberrations. Okay, it's the same. Sorry, hang on, back up. I'm going to see what slide I'm looking at. Pardon me for a second. I need to stand back. Okay, let me go here. So, what limits TEM image resolution? First thing I was talking about is the probe. Now we've got an image, and I want to get a high-resolution image. What's limiting the resolution here? What's the fact that we have a sample, we have electrons scattered through the sample, they're scattered through certain angles. Those scattered electrons now go through another lens system. This is supposed to be a series of lenses, okay? And just like in the probe forming system, where we have an angle-related aberration, we have an angle-related aberration not from the probe, but now from the electrons that are scattered through the sample. How do we minimize that? What do we have to do? We have to minimize the spherical aberration or the chromatic aberration. Okay? So we got to minimize that. What kind of resolution can we expect? Now, here's where you have to understand your microscope. You have to understand what kind of microscope you have, what kind of lenses you have. Do you have a conventional microscope with conventional lenses, conventional round lenses, or do you have what's called an aberration-corrected microscope? And we'll talk about both in a minute. So let's first talk about a non-aberration-corrected microscope, a standard microscope. Okay? We can go through and derive a bunch of equations, and I'm not going to do that for you. But I can tell you that we can derive an equation that says the best aberration that you're going to get, the best resolution that you're going to get, delta, is going to be 0.6 times CS, the spherical aberration coefficient of the microscope, times the wavelength of the electron to a power. Okay? Now, what does that tell you? Let's first look at, remember, lambda is the wavelength of the electrons. Higher energy electrons have lower wavelengths. If the wavelength is lower, the resolution is smaller. So you can take a standard microscope, and if you want to get better resolution, what do you want to do? You want to make the wavelength smaller. Why? Because this is to a 1/4 power, that's to a 3/4 power. So in the past, what used to be done To get a higher resolution image, you would simply go to a higher voltage microscope to give you a smaller wavelength. Okay? So you would start with original microscopes tended to run around 100 kilovolts, and then they started to go to 200 kilovolts, then 300 kilovolts, then 1,000,000 volts, and there's actually a 3 million volt microscope. Okay? It's, the 3 million volt is still in Japan right now. Okay? There are very few 1,000,000 volt microscopes anymore. Most of those have been retired, I guess is right, or decommissioned, right. There's still 1,000,000 volt microscopes in Japan. In the US, I think there's still one left. There used to be 4 or 5 in the US. There's now one left that I know of. It's out in Colorado, I believe. The one at Argonne was decommissioned about 15 years ago. The few other ones were mainly Berkeley's 1,000,000 volt microscopes were decommissioned about 10 years ago. Everybody's gone to a different type of solution for doing higher resolution studies. There are other reasons for going to high voltage microscopes, but that's a different story. Okay, so what does this graph tell us? This gives you a sense of what kind of resolution you can get for different accelerating voltages. So what have I done for you? I've done a calculation for different values of CS, what kind of resolution you can get at different voltages, okay? So if you wanted 1 angstrom resolution, okay? If you wanted 1 angstrom resolution, what kind of CS do you need to get 1 angstrom resolution at different voltages? So at 1,000,000 volts, you only needed a CS of about 1 millimeter, okay? But if you're running down at 200 kilovolts, let's say even 100 kilovolts, to get 1 angstrom resolution, you need a CS in millimeters of 0.001, okay? What's a realistic CS value? Typical CS values nowadays are in the order of, for a conventional microscope, are somewhere around a few millimeters. So is this practical for doing anything? No. We won't build a single lens electron microscope with these sort of CSs anymore. It's not practical. Okay? What you'd have to do is either change the wavelength or somehow decrease CS. Okay? Now, a single lens microscope, you're not going to do that. The new generation of aberration-corrected microscopes do that for you. And we'll get to that in a minute. And what's happened there? What's happened is, over the years, we've slowly gotten either better in CS or higher voltages. So when we compare resolution over the years as a function of year, optical microscopes reached a limit, roughly in the 1920s. They haven't gotten much better. Electron microscopes, remember I told you, started roughly in the 30s, and they slowly got better and better and better, and then they finally reached a limit. That limit was how good we can build a single lens. Around the year 2000, okay, we started getting a new generation of lenses. That is aberration-corrected microscopes, where what we've done is we've realized what the limitation here is, and the limitation is the lens design. With a single round lens, you cannot eliminate CS. It's impossible. You can prove that mathematically, and it's been done years ago. What you have to do is we have to get rid of spherical aberration. We have to get rid of spherical aberration is by redesigning the lens system. And let's see, what's the next slide? Yes. Hang on. Let's see where we are now. Yeah. I'm going to skip this for a moment. I want to skip forward a few slides. Here we go. Sorry, I had things out of place for a minute. So how do we get rid of spherical aberration? Spherical aberration comes from the fact that we have a round lens. Okay, because we can never get, in a round lens, you can never have a lens that defocuses. You always have a condensing lens. Okay. What we've discovered, or what was discovered by mainly here, there are several people that did it. Albert Crew thought about it years ago. Harold Rosa really developed all the technology for it, and he discovered how to make a non-spherical lens, which is a negative CS lens. Okay, if you take a positive CS lens and a negative CS lens, you can now make CS near zero. Okay, and what that is, it's a series of round lenses surrounded by hexapole lenses. This is a very complex lens system now. It's no longer a single lens to focusing, but it's a group of lenses, okay? I'll show you some images later of what a image correcting microscope looks like. It no longer has a single objective lens. It has, depending on which microscope you're looking at, somewhere near 100 lenses in it, okay? And 100 lenses, it gets very complicated to align and do it. One of the reasons that it took so many years to get aberration corrected microscopes is that we couldn't physically manually do all the corrections. Once we got the computer control and the computer processing power and the digital detectors, we're able to do all these corrections semi-automatically. They're never perfect. You still have to do some of it yourself, but it's speeded up the process enormously. Okay. So what's happened again is we've gone from single lenses to multiple lenses, and those multiple lenses consist of a round lens, quadrupole, hexapoles, octopoles, dodecapoles, and what they do is they take a lens that had aberration coefficients and they bring all of the lenses back to have a single focal point. And now CS goes to near zero. In fact, we can even make CS even slightly negative. What does that mean? It means we can take an image that looks like this and actually get down to half an angstrom resolution. Remember, I told you a few minutes ago, let's go back. Back to here. Conventional resolution, if we go back in the 90s, was in this range. You know, 1 to 3 angstroms was just about doable. But in order to get 1 angstrom, you really need a really small CS, and that wasn't practical. Okay? It's only when we started to get CS very small, by using very small angles, that we started to get resolution limits in the angstrom or sub-angstrom regime. Okay, let's go forward now. Question? Yes? I'm sorry, wait a minute. I got to get a little closer because I don't hear well.
CS unit is mm or micrometer you have given. What that actually means? Where is that comes from?
Millimeters?
In the microscope, I must.
Yeah, it's so the question was, where does the CS come from? How is it measured? I always gave it in millimeters, okay? It's a function of the focal length of the lens and the gap in the lens, okay? The pole piece gap, the space between lenses. Typically, the focal length and the CS are about the same, and the typical focal lengths in the objective lens are related to about a third of the gap. The typical gaps, space between the pole pieces, is, depending on whose microscope you get, could be anywhere from 1 millimeter to 8 millimeters, okay? More typically, I think the gap you have, I think you've got a Titan Super Twin, right? So you've got about a 5 millimeter gap, okay? The way high resolution used to be done was 2 ways. It was either increase the accelerating voltage because CS was constant, or decrease the size of the gap, make the gap smaller, which changes the focal length, which changes CS. So if we make the gap smaller and smaller and smaller, CS gets smaller and smaller. Okay, at a certain point, if the gap goes to 0, CS will go to 0, but then you can't get your sample in. So there always has to be a gap. So the high resolution microscopes that we used to have in the past used to have very small gaps, so very small spaces, and you would just barely get the sample in. But when you get in those configurations, you can get a sample in, but you can't do anything to it. You can move it a little bit. Can you go up and down a little bit? Not much. Can you tilt it? Almost none. Okay? Nowadays, the kind of material science experiments we do tilting experiments. So you want to be able to tilt the sample. What's a good number? You'd like to tilt at least 45 degrees, ideally maybe 60 degrees. Okay. If you're tilting something 60 degrees, think about it. If your sample is 3 millimeters in diameter and you're tilting by 60 degrees, you need a gap that's what? Cosine of 60, so you need a gap of near 5 millimeters. Okay, so 5 millimeter gaps, like we have at the machine here, is about standard. 5 millimeter gap, your CS is going to be a couple of millimeters. Okay, so you're not going to get better than that because of the gap. Okay, did that answer the question?
Yes, but CS value is not just the gap. It is actually that.
It's a parameter.
1 millimeter is the gap plus something you told, a focal length of.
CS is CS is a numerical parameter that we use to calculate the parameters of a lens. It happens to be a constant, okay? And that constant is related to the design of the lens. Lenses with large gaps have large CSs. Lenses with small gaps have small CSs, okay? Let's put it that way. The other way to relate CS is the CS is, not only is the gap related to CS, but the gap also is related to the focal length of the lens, okay? So my way of thinking is the focal length is related to the gap. The bigger the gap, the bigger the CS, the longer the focal length. The bigger the focal length, the worse the resolution of the microscope is. Does that help? Good. Good question. Thank you. All right. Let's see, where are we? We're talking about, corrector, excuse me, I need a drink of water for a moment. And I just need to go back to see where I was. That's forward. Yes, so we talked about correctors. Good question about CS, where it came from. The CS comes from the lens design. The bigger the gap, which means more space, which is what we want to do for doing experiments, the worse the resolution. What do we have to do? We have to get rid of CS. How did we get rid of CS? With a conventional lens, you can't. You only have to either change the accelerating voltage or make the gap smaller. We want the gap bigger. So what we've gone through is develop new lenses to give us a round lenses always have a positive CS. Other lenses have a negative CS. By adding other lenses to the round lens, we can now get a net CS which is near zero. And nowadays, because of the number of lenses we add, we can actually make CS negative overall. Okay. And what does that mean? It improves the resolution of our microscope. We now have microscopes that can routinely do 1 angstrom resolution with a 5 millimeter gap. The machine you have downstairs should easily, it's a 300 kV? 300 kV super twin with an image corrector, right? You should easily be able to get to the 1 angstrom regime with that machine, okay? What does that mean? That means we can get images where we can actually image single atoms, okay? And I'll show you other images in STEM later that show you even better resolution. All right, so we can make these correctors. Now I talked about aberrations of lenses. That holds for all lenses. All lenses have aberrations, whether it's in the probe forming system or the imaging system. Modern microscopes today, you can buy a corrector. Costs a lot of money. A corrector costs about $1 million. In addition to the cost of the microscope, okay? So you can put a corrector on the probe forming system, on the imaging system, or on both. So now if you put it on both, that's the cost of the microscope, $1 million plus and $1 million here, that's another $2 million on top of everything. So here we have just an image corrector, right? Okay. The instrument I have back at Argonne has a probe corrector only. I don't have an image corrector. It all depends on the kind of work you want. There are a lot of microscopes that have double correctors. Okay. It's very expensive and very tall. An example of, I think I'm going to just show you some pictures of correctors now. So this is the electron microscope at the University of Manchester. So what we have is a field emission gun. We've got condenser lenses, and then we have something that's as big as all the condenser lenses as the probe corrector, sample, and then no image corrector. Okay. Let's go. Okay, why do we want to do, what limits our resolution in a microscope? One of the things that limits the resolution of a microscope is, I'm going to go backwards now. I want to go back to this slide. Okay. If we want to do a high resolution image, we want to transfer the information from the sample onto our detector. And that information has to go through a series of lenses, okay? And I already talked about aberration correctors to minimize the aberrations. That'd be great, okay? So we talked about that. I'm going to go forward now. The thing we have to worry about is that we have information that's generated at the bottom of the sample, and it's got to get transferred through a whole series of lenses to a detector. In that transferring process, we're going through a number of lenses, and each one of those lenses contributes to the contrast. Okay? What does the aberration corrector do? The aberration corrector minimizes the oscillations in the image that happen due to the various focal points of the lenses. Okay? So what happens when you have a microscope that is non-corrected, so just a standard microscope, okay? The information, the phase contrast transfer function, the information that's transferred depends on the resolution you're trying to get, and at a certain point, information is no longer transferred. So that's called the resolution limit of the microscope. And that can be determined basically by CS. Remember the formula I told you? 0.6 times CS to the quarter lambda to the 3/4. That defines that angstrom limit, okay? Resolution limit. Now, if we want to go to better resolution, what do we have to do? We have to change CS. Okay? We can do that by putting an aberration corrector in, which reduces CS. If it reduces CS, it extends the contrast transfer function to a new resolution limit. Okay? This is a conventional microscope. This is an image-corrected transmission electron microscope. Notice that we've moved this down in frequency space. This is angstrom resolution now. If we wanted to get half an angstrom, we can move it further down. Okay? If I wanted to move it even further, I have to correct not only the spherical aberration, but also the chromatic aberration. Okay? And if I wanted to move further, we have to decrease the energy spread of the source. So we can do that two ways. We put in a different source, a field emission gun source, or we put in a field emission source with a monochromator to reduce the energy spread even further. And that's how we move this even further. Today, we can also build a corrector to correct for chromatic aberration. That's a very complicated device.
Can I ask a question?
Sure.
Suppose if you just put a monochromator,
Yeah.
even without correcting the probe, will it be of some use?
So the question was, if we put a monochromator on a machine, even without a spherical aberration corrector, will it be of any use? And for high-resolution imaging, will it improve it a little bit? Yes. The corrector would be, spherical aberration corrector would be better. Okay? Now, a monochromator on top of in your probe forming system will give you other opportunities. So there's other things you can do with a monochromator that would be beneficial. If I was going to give my druthers, if somebody said, what should I put on? Should I put a monochromator or an aberration corrector? I would say put in an aberration corrector. Where would I put the corrector? Would I do an image corrector or would I do a probe corrector? That depends on the kind of experiment you want to do. Okay, if you're interested in having small probe work and doing analytical work where you're interested in a small probe, the probe corrector is better. If you're interested in doing high-resolution imaging, high-resolution TEM imaging, then the image corrector is better. Okay. Could you put both in? Sure, but that gets really expensive. Now, there are people that, if you have a funding agency that'll do it, go for it. Okay. Okay. I was going to say, in addition to doing the spherical aberration, we can put chromatic aberration correctors in. Those are even more complicated devices than a simple spherical aberration corrector, which only has maybe 50 or 60 lenses. Okay, I'm probably exaggerating there, but it's a lot. In a chromatic aberration corrector, you not only have to have spherical aberration, but now you also have chromatic aberration. And the only way you can do that is, in addition to having electromagnetic lenses, you have electrostatic lenses. Okay, so you have a combination. So it's both voltage, electrostatic lenses and electromagnetic lenses. And now you can correct both. Okay, this is what a CS plus CC corrector looked like. And you notice it's 83 centimeters tall. And this is the one that's got, let's see now, here we go. These are all the lenses. This is just the corrector, which is that bit. And you can count how many lenses. These are just the main lenses. There's additional lenses on top of it. And you notice, if you had to manually adjust all of those lenses by hand, can it be done? The very first ones were done all by hand. Yeah, the very first CC corrected machine was done all by hand. Yeah, rapidly learned that they're not going to do this by hand very often. But, so this is one of my colleagues, J.G. Wen, back at Argonne. This is the world's first CC CS corrected microscope. It's still at Argonne. It's about 10 years old now. It's about to be decommissioned. If somebody wants it, they'll sell it to you as a used machine. It's a really complicated beast. But it was a 300 kV. It had a 5.4 millimeter gap. And it did a really good job. Just to give you a sense of what the resolution change was, this, again, remember, this is the phase contrast transfer function. Where this goes to 0, that usually the resolution is defined by the first times we cross 0, okay? And so the resolution of this type of machine without a corrector was just about 2 angstroms. With the CS plus CC corrector, it got down to below half an angstrom, okay? All right. And what that means is we can get very good resolution even at lower voltages. So at 80 kV, we've gotten down to 1 angstrom level on that. That was the first on that particular machine. This happens to be my machine. It's a 30 to 300 kV probe corrected machine, okay? So my probe corrector, remember in the other machine I showed you at Argonne, is an image corrector. It's all down here. Here I have conventional lenses. My probe corrector takes up that amount of space. It's a little bit smaller because it's only CS, it's not CC. What I've decided to do is instead I put a monochromator on. So I have a probe corrector plus a monochromator. And that allows me to get probe sizes. And this is a real image from my machine. The spacing of these 2 atoms, this is a gallium nitride spacing. You can see the space between those 2 atoms. There's a line between them because they're separated. That spacing is 63 picometers, okay? Okay, so that means I have a probe size that's probably about 50 picometers, okay? And with that I can do not only imaging, which is nice, but I don't do imaging, I do mainly spectroscopy. Okay. Now we've actually gotten farther than I thought we would get, so let me just see. I've talked about a lot of things. I'm going to give you a few references now. These are going to be in your notes, so if you want to know some, I talked a huge amount of things. I covered a lot of territory, and I'm getting dry, so it's getting to the point where I need to stop talking, and that's good because I'm getting near the end of these slides. Some basic references on electron microscopy. We'll be using a lot of these later in the talks later about defect analysis and diffraction techniques. Okay, now I think it's about noon. So we're finishing a little bit early. But to be honest, I need a break. Let's see, what else do I have here? Yeah, why don't we take a break now? When do you want, let's just stop for the morning now. Mainly because I need to stop talking. I'm getting hoarse. We can start at 2, is it okay? That's fine for me. Does 2 o'clock sound okay? Take a break? Yeah. When we come, sorry. I do need a break. When we come back, we're going to start talking about, so we're done talking about the instrument. So what did we talk about today? We talked about the electron sources, okay? We talked about the lenses. We talked about aberrations in the lenses. We talked about the functions of apertures. We talked about beam control, stigmators, how to adjust stigmatism, how to adjust focus, how to recognize when you're in focus, how do you recognize when you have an astigmatic image. We now talked about the functionality of the instrument. We didn't talk about things like vacuum systems. That's a whole nother talk. We didn't talk anything about sample prep. That's a whole nother topic. When we come back from lunch, we'll start talking about actually using the microscope. So far I just showed you examples. We're going to start talking about first electron diffraction in the microscope. So I'll give you some basic feed-throughs on what electron diffraction is and how we get information from electron diffraction. And then Hamish is going to come in and talk about some advanced diffraction technologies for doing microstructural analysis and defect analysis. That will cover all of the afternoon. So we'll talk mainly diffraction this afternoon. I think that's right. Let's look at the schedule. And then tomorrow morning, I think we're doing imaging. Is that it? Hold on. Let me go back and look. So I'm going to cheat here because I don't remember anymore. Microsoft would like to access my camera. No, don't do that. Don't allow. I don't know why Microsoft. I need to go back to our first slide. Come back. Uh-oh. Microsoft doesn't like me. Well, I was going to show you something. Oh, there we go. Let's go all the way to the back. Yes, diffraction this afternoon. Tomorrow morning we'll talk about imaging, and then we'll talk about spectroscopy tomorrow afternoon. Okay, so diffraction this afternoon. I'll start out on basic select area diffraction, basic diffraction information, and then Hamish will talk about the advanced diffraction. And then tomorrow we'll talk about imaging and contrast, defect analysis, and then inelastic scattering tomorrow afternoon. Okay, so let's take a break now. Come back in 2 hours, like you said. All right. Let's see, what is it? Nanri, is that right? Nanri, thank you. I'd like to back up just a little bit, because when I went back to the room, I was not happy with something, because I was rushing. And I'd like to just go back to the aberration corrections for a minute, because the aberration corrector is important. And you remember this slide that I showed you before about the two types of aberrations. Yes, presentation mode. Just take a moment. Oops, back up. You remember this slide that I showed you a minute ago? I added some words well, over lunch. And I added this because when I was doing discussion, I was rushing, and I should have said I want to divide aberration correction into two regimes. One regime is before the specimen, and one regime is after the specimen, pre and post. Now, the corrections, the ideas are the same. We have spherical aberration and chromatic aberration, okay? And I was rushing through it, and so I want to just go over just a little bit more about the correctors, okay? So the first corrector that I talked about, this figure, I just added this small drawing. I want to talk about this corrector in pre-specimen. So if this is our entire microscope, I'm going to talk just about a corrector on the probe forming system, okay? And you see it here. So I'm talking about the ability to form a probe and to form a small probe. Now, this general curve that I showed you relates how we create a probe. And there are three limiting factors. There is something called the diffraction limit, the brightness of the gun, the spherical aberration, and the diffraction limit, okay? So one of which is how small of a probe can we form? It's called a Gaussian probe, D sub G. And that's related to the amount of current you want, the brightness of the gun, and that angle, convergence angle that we did. So that's one fundamental limit. You can't change that. The second limit is related to the aberration coefficients. It's also related to the angle of the beam, but instead of being linear, inversely to the first power, it's inversely to the third power. And it's controlled, this is just controlled by the gun itself. So this is gun related. This is lens related, okay? And there we have the angle of the beam and also this aberration coefficient, CS. And then there's finally something called the diffraction limit. You're forming a probe, it has a certain wavelength, and we have a certain angle, okay? So if you look at these three are shown in the three curves here. The blue curve there is the fact that you've got a probe of a certain beam current and a certain angle. And as the angle gets larger, we can make a smaller and smaller probe. So ideally, with a very large angle, the probe should be able to get smaller and smaller. However, because of spherical aberration is zero for very, very small angles, but it gets larger as we go up. So we have one coming down, the other coming up. There's a relative minimum there, okay? And so this is only in the probe forming system, okay? So these are the three limits, the Gaussian or geometric limits, D sub G, the spherical aberration limit, and the diffraction limit. Generally, it's this one and this one that control how small of a probe you can get. So if we want to make that probe smaller, what can we do? Well, what we want to do is we want to get the probe as big an angle as possible, right? If this is the limit, the bigger the angle, the more convergent the probe is, more like that, the smaller the probe should be, except spherical aberration increases. So that's the limiting factor. So the whole idea of aberration correctors for the probe forming system is we want to make CS as small as possible so that this curve moves this way, and we can move it down and down. And what that does is if we can move this red curve this way, this minimum slowly moves this way, and our probe size gets smaller. All right. Now, and that's what I was trying to show you here. How can we make the probe smaller, well, we have to get rid of this. When we think of a probe, what we have to think about is, here's our electron beam, and there's a tail around it, okay? If I did a line scan through here, here's my probe. I'm making a line scan across here. We see we have a very sharp peak, but it's very long tails. You might ask yourself, well, what of the tails? It depends on the information you're trying to get. And we'll see later, if we're only worried about an image, we only worry about this information. If we're worried about spectroscopy or other information, where a few electrons create a lot of signal, we worry about something out here. So, do I want a very sharp, very intense probe? Well, this is a very sharp, intense probe. It'll give me a nice image. But the tails, this information out here, is a lot of signal which can create other images and actually complicate our images. So ideally what you want to do, you want to get rid of these tails. 2 ways to do it. Put a smaller aperture in. I put a smaller aperture in here, do a line scan through here. Here's my probe now. Those tails are now gone. But the probe is fatter. I make an even smaller aperture, I can even make it smaller. This is a sharper probe, but this is a fatter probe. Question, which one of these will give us the better information? Depends on the experiment we're doing. If all I'm caring about is an image, I'll go to this one. If I'm caring about doing high spatial resolution where all of the electron, I want to concentrate all the electron signal, this is the better probe. Okay. So I was trying to make that difference. Now, the other aberration is, and I added some words to this slide too, and a figure too, the post-specimen aberrations. Okay, so what limits, so one we talked about what limits the probe before the sample. What we now want to worry about is what limits the signal that we measure after the sample. Okay, so previously I was talking about these lenses. Now I'm talking about these lenses. I'm sorry I didn't explain that better earlier. All right, so we talked first about the illumination system. Now we're talking about the imaging system. All right, now this is the part that we have to think just a few minutes about. So this is our sample, there's our sample. So now I'm talking about what's happening here. So the beam comes in, hits our sample, and we get scattered electrons from here. These electrons go through lenses. These lenses have aberrations, okay? So we have spherical aberration and chromatic aberration going through the post-specimen lenses. Now, this is very complicated because there are multiple lenses here. Generally, what one says is when we want to interpret an image, what we're looking is we know what's coming in and we're measuring what's going out. Ideally, what we want is the structure of what's inside, and when we talk about imaging tomorrow, we'll talk about that. What I'm worried about here is, okay, this is what's coming out. That's great, but that's before I hit any lens. Now we have to go through the lenses of the microscope. So what we actually measure, psi, is not what comes out of the sample, but it's something that's multiplied by a function which we call the contrast transfer function. Okay, and I'll just call it T here. Okay, so this contrast transfer function incorporates all of the effects of all the lenses. In order to, ideally, this is what we want, but this is what we measure. So what we want to do is understand the transfer of information from point A to point B, okay? Do we have, if anybody's here an audio expert, right? You know, audio systems, you have fancy amplifiers with lots of correctors like he has here, and you probably have better ones at home. All those things amplify and correct for the distortions of the microphones and the speakers. Well, this is the same thing. There's distortions in these lenses, and that's all described by this function called the contrast transfer function. Now, this is the slide I skipped. Oh, no, sorry, this is not the slide. So all of these lenses are all of the aberrations from all of the lenses after the sample are in the contrast transfer function, CTF. All right, now here's the complicated one. I was trying to avoid talking about this because it's a complicated equation. I don't want to derive this equation for you. This is the equation that describes the transfer of information through a whole series of lenses, okay? It's a mathematical expansion, let's not worry about it, but it's a function of many parameters. It's a function of the various aberration coefficients, it's a function of the wavelength of the electrons, it's a function of the focuses of the lenses, and it's also a function, and I apologize, but I've changed notation here, it's all a function of angle, okay? So what happens is this function is plotted here in blue, okay? And I'm plotting it as, this is the contrast transfer function as a function of resolution. All right. If you had no aberrations in a system and you put something out of the microscope, if there were no aberrations, it would come back, whatever here would appear here. That would be a contrast transfer function of unity. No losses. But in reality, because of all the terms in here, which consist of defocus, spherical aberrations. I use CS in the previous equations. Sometimes it's called C3 because it's the third order. And then there's higher aberration coefficients. It's also a function of the energy of the beam, and it's function of the scattering angle, Q. Again, that should be alpha in the other curve. All right, so a perfect lens would have a perfect contrast transfer function, to be unity. In reality, it's never unity. For very low frequency, very large objects, an electron lens is pretty poor. It actually cuts off. The transfer is bad. Then there's a region where it's relatively high, and then it drops off again. Conventionally, the resolution limit of a microscope is usually defined at the first crossover of 0, this point right here. So how can we move this point this way? We move this point this way by adjusting the aberration coefficients, okay? So this is a contrast transfer function plotted for one set of coefficients. If I want to make this better, I want to expand this so I can get higher resolution, what do I want? I'd like to have something that's flat, and I'd like to have something that's flat to infinity. That'll never happen. But I want it as flat as far as possible, and I want that first 0, the first crossing, to be here. What do these oscillations mean? These oscillations mean the contrast in the image is changing. So let's pretend this is dark contrast, this is white contrast. So now I'm getting oscillating contrast. I don't want that to interpret an image, right? I want to have something that should be white always to be white, something that should be black to always be black. So we want this region as big as possible so it's uniform contrast, okay? So that's what the contrast transfer function tells us. And by adjusting, we can do this calculation by putting in the various parameters and see what value of focus, C1, what value of CS, which is C3 here, what energy of beam, so the wavelength of the electrons, and what scattering angle we need to move this as far this way as possible to get us the highest possible resolution and the flattest possible contrast, okay? I'm going to skip that curve for a minute. We'll talk about it later. And this 0, this point right here, can be defined. We can set, when do I get a 0? Where's the first 0 of this? That's how this equation comes out. Setting that to 0, solving, we can solve and we can say that first 0 occurs when at 0.66 times CS to the quarter lambda to the 3/4. Okay? That's how this equation came out, by solving for where that 0 is. Okay? And again, in the previous equation, it was C3, here it's CS. Depending on who wrote the equation and when it was written, it's either C3 or CS, okay? Okay, so that's, I just wanted to go back to that. And I've corrected it in the notes, and when you get the PDFs, it'll be corrected in there, okay? All right, so now I'm going to leave the instrument per se, and if this works, we're going to go to, where is this one? I hope this works. Yes, reminder, send your email information to Varun. All right. So up to now, we've only talked about an instrument. We've talked about sources, we talked about lenses, we talked about aberrations and deflectors and all. That's just to get you familiar with the machine. All right. I gave you a lot of information in, what, an hour and a half, 2 hours, maybe 3, I don't know. Very difficult to absorb all of that. That's why you're getting the notes. That's why you also have in the notes is my email address if you have a question. And I also gave you the reference books to look at things. Now, let's change gears for a minute. We want to now actually look at not the instrument, but the information from the instrument. What information can I get about my material, whatever it is, to characterize it? Because that, remember the very first set of talks I gave, we have a problem, we want to get an answer. We have to ask ourselves, so what kind of information is available? Now, there's two kinds of information. Well, there's 3 kinds of information that we can get. We get morphological information, shapes. That's an image. We can get crystallographic information. That'll be in from diffraction. And we can get spectroscopic or elemental information. Okay, so that's the next 3 tasks. So this afternoon, we're going to talk about diffraction. Tomorrow morning, we're going to talk about imaging. And tomorrow afternoon, we're going to talk about spectroscopy. Okay? So we're done with the instrument now. We'll probably say something about the instruments in between, and we'll go from there. All right. Now, there's lots of ways to talk about how a microscope gives you information. Some people start talking about imaging first, and then they go to high-resolution imaging, and then they go to diffraction. I'm going to do the inverse. I'm going to start with diffraction. Then we're going to talk about imaging and high-resolution imaging, okay? And then finally, spectroscopy. All right, why do I want to do that? Here is an image and a diffraction pattern, okay? Let's look at this first. What can I tell from this image? Well, I look at that and, okay, this is a hole, so there's nothing here. Good. There's something long and skinny, and there's something that's mediocre. Does that tell us a lot about the sample? No. It does tell us something about the shape. I have some long and skinny things in it. Something that looks like if you smoke a cigar. So what? What is the question that are you going to ask? What's the information you need? I really want to know, what's the difference between P and M? It just reminds me of Delhi. Let's see if we can break the record. Do we want to break the record for 17? The information in an image is only limited. And why is that? It's because when we take an image, we're only taking a small amount of the total scattering that comes out of the sample. That's why diffraction is very powerful. What do I like to use? Do I use imaging? Yes. Do I use diffraction? Yes. Do I use spectroscopy? Yes. And we're coming up slowly. There we go. So, looking at this, I have a little bit of information that's solid. But if I look at now a diffraction pattern, let's worry about how I got it in a minute. I look at a diffraction pattern from M, I see a certain structure in that solid. Okay? I look at the diffraction pattern from P, and I see it's completely different. Okay? And you will see in a little bit that we can analyze this and tell something about what this is. This would be an FCC matrix. This is an M23C6 precipitate. I can measure the crystal structure. I can measure the lattice parameters. I can tell you something about this that I can't get from that simple image. So the message here is don't ignore diffraction. It is extremely powerful. It gives you a huge amount of information solid. It does take work to analyze it. It's a lot easier to look at an image and say, oh, I have a cigar and a flat thing. So what? Okay. Let's talk about now, how can we get information out of that? And let's see, are we still in? Yeah, we're still in the right mode. Let's go forward. Here's another example of images and a diffraction pattern, both from the same thing. What can we tell about here? Well, we look at this and we see, oh, this area is a lot different. We have long skinny things, not quite cigars, and we got some flat guys in a matrix. And now we do diffraction from this, and what do we see? We have a diffraction, and this diffraction is telling us several things. We've got major reflections, which is mainly from the matrix, you'll see later, and we've got very fine detail in that pattern. Those come from the precipitates. And by analyzing the diffraction, we can tell what the structure of those precipitates are. Now, Hamish, who's coming in a little, he'll be here in a little bit, will be talking more about advanced on how to do some of that. I'm going to give you the overall view of electron diffraction, okay? Okay, so when we talk about electron diffraction, we've got a probe coming down, it hits our sample, and then there's electrons that are scattered. When I worried about doing diffraction, I'm not touching the condenser lens much, I'm forming my probe. My objective lens, which forms the first image, is running at constant excitation. And when I'm doing diffraction or imaging, what I'm doing is I'm varying the final lenses of the microscope, what's called the diffraction and intermediate lenses. Okay? So if I draw the optics of it, so our sample's sitting there, okay? We have a series of lenses after the sample. So we got the objective lens that surrounds the sample. That's basically here, it's the objective lens. The objective lens doesn't change when we go between imaging and diffraction. It stays constant. It has two characteristic planes. It has an image plane and a back focal plane. Okay? When I want to get an image, what I have is I adjust the post-specimen lenses to take that plane and move it down to my screen. That gives me my image. Objective lens doesn't change. When I want to get a diffraction pattern, all I do is I change the strength of this lens, the intermediate lens, or it's sometimes called the diffraction lens, and instead of looking at the image plane, I look at the diffraction plane. Okay? And now I have a diffraction pattern there. If I want to magnify something, I don't adjust this lens, because this lens is looking either at the image or the diffraction pattern. I adjust the lenses after it to give me a bigger image or a bigger diffraction pattern. Okay? So when you push a button that says D, or diffraction, all you're doing is adjusting this first lens to look at either the image plane or the back focal plane. When you when you turn a knob that says magnification, you're adjusting what's called the projector lenses, the final lenses, to give you a magnified view of what's ever at the next plane. Okay? All right. What's special about electron diffraction? Let's talk about that for a minute. Okay. It's one of the, to me, it's one of the most important features of a TEM. Okay? It gives us the ability to determine crystallographic information about the sample. We can determine orientation, we can answer simple things. Is a sample crystalline or not? Yes or no? Okay. Crystalline meaning an ordered structure of something versus amorphous. I keep turning that on. I shouldn't touch the screen. Answer is yes. You'll see that in a little bit. Is it monocrystalline? We'll show you that. And what's the orientation of the specimen relative to everything else? Okay. And Other question, is there more than one phase present? Yes or no? Okay, to understand diffraction, we have to go back to a little bit of physics. And the first thing I want you to think about is, I've got a single atom sitting here in free space. Okay, and I'm going to hit it with an electron beam. Okay, so here's my single atom. Electrons are going to hit it, and they're going to scatter. And they're going to scatter with different angles. First thing what you need to know is the intensity of that scattered radiation from a single atom goes as the square of the structure factor, f of theta. F of theta is a function of the material we're looking at. Okay? It's a function of the energy of the beam. It's related to the beam. It's related to the wavelength of the electrons. Okay? It's related to the atomic number of the atom. Okay? And it's related to the angle that we're measuring. So, what's the first thing to? High Z materials have high scattering. Low Z materials have low scattering. So if we just compare intensity now, remember the intensity is the square of this number. So high Z, gold, high intensity scattering. Low Z, aluminum, low intensity scattering. There's an angular dependence. Higher Z materials scatter to higher angles. Lower Z materials scatter to lower angles. All right. So you can write this down, and that's fine. But in the real world, you never look at a single atom sitting in free space, right? You could. I mean, in principle, you can get a single atom floating across your screen and grab a diffraction pattern from it. Difficult, but not impossible. In the real world, what we usually have is a collection of atoms. Okay? They're collected into some sort of structure. It may be a liquid, it may be a gas phase, it may be a solid, but they're a collection of atoms. And if we have, and I'll call this collection amorphous for the moment, meaning that there is no structure, the atoms are just jumbled together, okay? That intensity distribution that we measure as the electrons go past that collection of atoms looks very similar to what we had. Remember we said for a single atom it was just f of theta squared. However, as soon as we put those atoms together into some sort of collection, there's a multiplicative factor in there. And that multiplicative factor has to do with the average interatomic spacing of the atoms. The more atoms they are, the closer packed they are, the more scattering you're going to get at a certain angle. So, if we were to look at a diffraction pattern, is there going to be some scattering distribution? The answer is yes. And remember, for a single atom, it just monotonically decreased. It's no longer a monotonic decrease. There's now a sinusoidal variation. And that sinusoidal variation is a function of the diffraction angle that we're looking at, and importantly, the average interatomic spacing of those atoms. So if I have my diffraction pattern and I measure a line profile through there, I can get information about the average spacing of the atoms in my solid. Okay. So that's, okay. Yeah, so I've just drawn you, here's my amorphous solid. This happens to be an example of amorphous silica, doesn't really matter. The atoms are arranged in some way. We've got a diffraction pattern from it. You notice we no longer have a monotonically distinct, this is a real diffraction pattern now, okay? If I did a line profile through there, I'm gonna see an oscillatory structure. By measuring the periodicity of this oscillation, I can determine the mean or average atomic spacing in the solid. Okay, let's go a step further. Let's take our disordered solid, this jumble array of atoms, and let's start adding some sort of ordering to it, or periodicity to it. So a perfectly random distribution will look something like this. As there begins to be some ordering, okay, what will happen is these, how should I call it, broad, diffuse rings will begin to coalesce. They will narrow. They will segregate. You notice this one, for example, was fairly wide. It's now broken up into two, okay? Done it again. I have to learn not to touch that. What's happening here? We've gone from a random array to a collection of finite. If we take our material, and so now I've drawn, this is an example of a nanocrystalline film of palladium. Okay, we saw it's still rings. Okay, if I let that film grow so that the grain size starts increasing, what's happening is that those rings start breaking up into spots, discrete spots. And if I let that grow even further until I get a single crystal, now those discrete spots come into a single array. So we've gone from an amorphous to a polycrystalline to a partially single crystal to a single crystal pattern. So these are the typical types of patterns that you would see in electron diffraction in a microscope, depending on what you're looking at. Let's see now. I think I will skip this slide. Okay. Let me give you a real example of that now. Okay. Here's a material that I have intentionally taken from an amorphous state to a crystalline state. So it's all one sample. We amorphized this area, and we left this one polycrystalline. Okay. If I take a diffraction pattern from here and compare it to a diffraction pattern from here, this is exactly what we see. Okay. So this is the diffraction pattern from the polycrystalline area. This is the diffraction pattern from the amorphized area. What do we see about this? Well, we see these very broad rings, and when what's going to happen is when the material crystallizes, we form the atoms that correspond to this general spacing start to order, and we form very discrete crystalline bands. Okay? And what I've shown you here is a simple line trace through there and a simple line trace through there. And you see that here. The polycrystalline area and the amorphous are the irradiated area. Okay? The way we made this amorphous is we irradiated it with high energy ions. That's irrelevant for what we're talking about here. Okay. So in order to talk more about diffraction, I have to mention a few things about crystal structures and crystals. Now, I'm going to say just a couple of slides about crystal structures and crystallography. That's a whole series of lectures. I'm not going to cover that. There's no way I can do that. But what we can say is when we have a periodic arrangement of atoms, where they're periodically arrayed, we call that a lattice. Okay? That lattice, that periodic array, can be arranged into something called a unit cell that describes the solid. Okay? What's on the next slide? We can describe the atoms in that solid by radius vectors and certain directions, A, B, and C, crystallographic directions. We can say the solid can be described by a unit cell, and that unit cell has parameters. It has lattice parameters in multiple axes. Okay? There are lots of different types of crystal structures, going from simple cubic to tetragonal, orthomic, triclinic, rhombohedral. I don't have time to talk about it, but you should know they exist. The references that I gave you have references on electron diffraction. And you should know that there are, in general, 7 different crystal systems with 14 different Bravais lattices. Why am I bringing all this up? Because when Hamish gets up to talk about advanced electron diffraction, he's going to be bringing up crystal structures and diffractions and Bravais lattices and the like. So you should know they exist. You should know that it's a lot of work to make sure you understand this correctly, and it's not something that we can cover in a lecture like this today. Okay? That should be a proper course in electron diffraction. Okay? The other thing to realize is that when you have crystals, crystals with a very specific structure, we can describe those crystals as having planes of atoms. I'll talk about planes quite frequently. I'll say this is a 110 plane or a 111 plane. That has to do with the description of where that plane goes through that crystalline lattice. Okay. Again, if you've got a question on that, let's talk about it later. But I will mention crystal unit cells. I will mention directions in the crystal. I'll frequently talk about A, B, C, or X, Y, Z. Those mean the 3 principal directions in the crystal when it's a periodic lattice. and I will frequently talk about different types of planes. For example, if I'm talking about a face plane, let's assume I have a simple cubic system. I'm talking about a face plane. Well, think about it. If I've got three axes, x, y, there's the x-axis, a plane on the x-axis. There's a plane on the z-axis. Do I have the y? Oh, yeah, there's the y. So there's the y, the x, and the z. You can see we have periodic planes. I can have diagonal planes. I can have planes going across the corner. So all of these relate to the crystal structure of the solid. I apologize for trying to give you all of crystallography in about 5 slides. But I need to make sure that we're all, you know what I'm talking about when I say, oh, I'm talking a 1-1-1 plane. It means a plane going through the crystal structure along a certain direction, or a 1-0-0 or whatever, okay? You will hear similar notation when Hamish starts talking. Again, a good crystallography course, a good X-ray diffraction course will cover everything you need to know about, well, no, probably won't. It'll cover some of the things you need to know about crystallography. Go forward. Uh-oh. It's stuck. Why aren't you moving? Uh-oh. What are we going? Okay, you will frequently hear me talk about planes, HKL meaning alpha, XYZ, nomenclature, and I don't know where HK and L came from. I don't remember that. It's always been HKL, and I don't remember why. We frequently have notations. The standard notation is when it's a bracket like that, we're talking about a plane. When it's a curly bracket, they're equivalent planes. When it's a square, that's a direction. And when it's a pointy direction, it's equivalent directions. So just notation. You'll see these kinds of notations on a lot of the slides I'll be showing in both the diffraction and the imaging. So just so you know where it comes from. All right, let's go back to diffraction now. I think most of you have probably done something called a Young's fringe measurement, okay? So what is a Young's fringe measurement? What you have is a plane wave of radiation, usually a laser or a light source. It hits an array of slits, right? And some kind of slit array. The waves that come through interfere. At a certain plane, we get an interference pattern, and it'll look something like that. Okay? That's Young's fringe experiment. All right? Electron diffraction is the same thing. The only difference is that we replace the slits by an array of atoms. And the diffraction effect is, in effect, the diffraction between the slits formed by the periodic array of atoms. So if you think of an interference phenomenon, that's what diffraction is. It's interference where instead of an array of slits or holes, what you have is an array of atoms. And it's the periodicity of the atoms gives rise to the interference phenomenon. So let's show you that in a different way. So now here's our array of atoms. They form planes, okay? And we have planes in the crystal. So here are 2 equivalent planes. Pretend they're the 2 planes here. We have an incident beam of radiation, which in this case happens to be electrons. But the electrons can be treated either as single particles or they can be treated as a wave. Okay? It's the wave-particle duality. We're not going to talk a lot about that. That gets us into the realms of philosophy and physics. Okay? So when we have a incident beam, plane wave coming in, interacting with planes, those incident beams can be diffracted according to Bragg's law. Do I have it on here? Yeah. They can hit the planes, be refracted, and come out. What we want to do is we want to look at the path difference between PO and D. POD is equal to n lambda times 2d sine theta. You can just work it out from simple geometry, okay? You know the wavelength, you know the angles, you know the d spacing. That's the equation you get. That's the famous Bragg's law for diffraction, okay? And we get constructive and destructive interference, and we get what's called a pattern at this point. What does a diffraction pattern look like? Here's a diffraction pattern from a periodic array of materials, okay? We've got major Bragg reflections, okay? Because this is a two-dimensional array, unlike the slit pattern that I showed you a few moments ago, which there was only one. Let's go back up. Let's back up. Yeah. Here, I only had a single dimension array. I only have a line of diffraction. If I had a three-dimensional array, I would have multiple arrays of diffraction, of interference, sorry, not diffraction. So this is a diffraction pattern from a periodic array in 2 dimensions. So I don't have just a single line, but I have an array. And you see, this one's actually pretty complex, because not only do I get major reflections, I see a lot of minor ones. And we'll talk about that in a few minutes. Okay. The major reflections occur at characteristic scattering angles. The intensity of the major reflections now is determined, remember the equation I showed you before, it was little f times theta, okay? Now that intensity is proportional big F times theta. What's big F? This is really now what I call the structure factor. There's the atomic scattering factor that we had before. This is an expression that reflects the periodicity of the atoms in the solid, okay? All right, so the intensity we get is the square of the structure factor, which is the square based on the sum of the squares of the individual scattering factors times the periodicity function. This periodicity function is related to the interatomic spacing in the solid. Okay, what kinds of diffraction patterns can we get? There's several times. We can get the ring pattern that I showed you, a spot pattern, and then something called a Kikuchi pattern. The ring pattern comes from either polycrystalline or amorphous samples, okay? We'll talk about those. Spot patterns, nice clear discrete spots, usually come from single crystal regions of a solid, okay? If you have an area that has 2 different single crystals, you'll get 2 overlapping spot patterns. You'll see that in an example. B and C, spot patterns and Kikuchi patterns, are often in the same pattern, in the same measurement. And you'll find, we'll show you in a few minutes, that the Kikuchi patterns happen from very thick samples. The spot patterns happen from everything, okay? Kikuchi patterns are due to inelastic scattering of the electrons. Spot patterns are mainly the elastic scattering, okay? Ring patterns, the most useful thing about ring patterns is the identification of phases in polycrystalline materials. Okay, so let's look at that first. So here's a ring pattern, or a polycrystalline pattern. Why did I immediately say polycrystalline and not amorphous? First thing I looked at, I can look at this pattern, and what do I see? I see very sharp rings, not broad, diffuse rings. If it's broad and diffuse, it's generally due to disorder in the solid, so it's an amorphous material. When the rings are very sharp, so these are the broad diffuse rings that we had. These are the very sharp ones. When they're very sharp, it's usually a polycrystalline material. The important thing to notice, remember, just as I told you that the periodicity of the diffuse rings was related to the spacing of the atoms, the periodicity of these rings is related to the crystal structure of the solid. Okay? Let me show you an example of that. Here's titanium oxide in 3 different phases: rutile, anatase, and brookite. It's polycrystalline. We've got ring, and I've just chopped the pattern up into different things. And what you see are, there's rings everywhere, and the rings change. They change because the crystal structure changes and the periodicity of the atoms changes. Okay? Can we analyze this? Yes. The way we analyze it is by measuring the spacing of the rings. Okay? How do we do that? We do something very simple. Okay? What we do is we're looking at a diffraction pattern. We can come back and say that diffraction pattern is due to a Bragg reflection, so either a beam is coming straight through, the straight through beam, which is that guy right in the middle, or it's due to a beam that's become diffracted and come off at an angle. One of these. Okay? So what do we want to, what do we need to know? We need to know a few things. We need to know what the radius of that ring is. there to there. Or equivalently, what I usually do is it's hard to measure a radius, it's easy to measure a diameter. Okay, why is it hard to measure a radius? Because it's usually pretty hard to find the center. This is usually very bright. So if you're doing a diffraction analysis, what I always do is measure a diameter. It's easy to find the biggest diameter. And I'll make a table of diameters. What we can show, and I'm going to draw you now a simple illustration of that diffraction event. We have a diffraction event that happens here. The beam comes down and hits the film or the detector, and there's a ring at a certain radius. I can draw this geometry out, and I can tell you that this forms a relatively simple geometric triangle, okay, where the radius, the length of diffraction from where the beam hit the sample to where it hit the screen, and the radius are very characteristic. That radius is proportional to 1 over the diameter of the spacing of between the planes. This length is proportional to 1 over the wavelength. Okay? If we take that geometry, we can show that the very simple equation describes it, namely the radius times the d spacing is equal to the length times the wavelength. This is called, sometimes L is called the camera constant of the microscope, or camera length of the microscope. That's where the L came from. Lambda, the wavelength, is the wavelength of the electrons. R is something you measure. D is the d spacing. So how do we use that to measure something? We have a diffraction pattern sitting there. We have an unknown. If I know lambda, and if I know L, all I have to do is measure R, and then I automatically have D, the d spacing. All right, so you put your sample in, you know the wavelength of the electron. Why? You know the accelerating voltage. I gave you the formula for calculating the wavelength. You look up on, somebody tells you, here's the camera length, and you've got the d spacing. So what did I just go wrong there? Somebody just told me what the camera length is. Don't trust it. Okay? So what you're going to do first is to calibrate. Exactly. Good. So how do you calibrate? You get a material that you know. Get yourself, you can easily buy polycrystalline gold, polycrystalline aluminum, some sort of a material, pure element that you know the d spacing for. Okay? So what we're going to do is we're going to put in a material that we know. This is an example from aluminum. I can look up in all the good books the lattice parameter for aluminum. I can calculate, knowing the lattice parameter and the possible reflections. Again, this means you know crystallography to know this. But I know that I'm going to have the following lattices in aluminum, 111, 200, all of these. These are the lattice descriptions that I know. I know the lattice parameter of aluminum. I can calculate what the d spacing is using this formula. There's the d spacing. I can go to my aluminum pattern. Because I know my crystallography, I know 111 is going to be the first ring, then 200, 220. I can measure each of these rings. So I know the d spacing. I know the radius, R. I've measured that in all of them. And I can calculate the camera constant, R times D. Okay? So I take R, I take D, and I calculate the camera constant. Notice it's nearly constant. It should be. All right? What's going to change? What will change is if I go to a different accelerating voltage or a different camera length. But that's now a constant. I've now calibrated my instrument for the conditions I've got. That's the magic number. All right? Now I'm going to go to my unknown sample. I think that's the next one. Yes. So this is one. I happen to know it was gold, but that doesn't matter. I put it in under the same conditions. I have my camera constant that I measured before. I measure my R's. From the R's and my camera constant, I can calculate, here's another camera constant. I can calculate the spacing. Okay? So that's how you would do a simple analysis of diffraction for a ring pattern. Okay, what's nice about these? Well, the ring patterns is characteristic of the planes in the crystal. It's, very importantly, it's calibrated for the magnification of the camera length you did. Most microscopes will allow you to change camera lengths, so you can make it bigger or smaller. You need to calibrate all of those. Another important thing, I'm going to go backwards now a few slides. This one. One of the things that's very important is this distance, the camera length. Now, you might think, what are the kind of camera lengths I work with? The camera lengths are typically hundreds of millimeters to thousands of millimeters. Okay, that's very important. But all of that assumes the lenses are working the same every time. It also assumes the sample's always at the same spot. Okay, so there's something called setting the eccentric height of the microscope. Who's ever training you on how to use the microscope will show you how to set that. You always need to make sure the sample's at the same position. You don't want it too low or too high, because that will slightly change the camera constant. It'll change the length. How much of it changes it? It depends on how much variability you have in your instrument and what camera length you do. You need to make sure you're always at the same conditions. Okay. Let's go forward. So once you've calibrated it, and you know the camera constant, L, you know lambda, and you know R, then you automatically have D. All right. Now, a simple set of formulas. You can look these up in all the good books on how you interpret the D spacing relative to lattice parameters and crystal structures. I'm not going to have time to talk about that, but this is all in any of the good books on X-ray crystallography, X-ray diffraction. You can look that up pretty well. All right, we've gone through this one already. Let's see what's next. Oh, that slide's repeated. That, or I'm going the wrong direction. Ah, yes. Now I see what I wanted to do. All right, so this was an example of polycrystalline material. What happens when we go from polycrystalline? How did I know it was polycrystalline? Remember the sharp lines? What happens when we go from polycrystalline to a single crystal? Okay, so I'm going to show you the same material first as a polycrystalline, and now here's the same material as a single crystal. What's happening? These individual rings are breaking up, right? The grain. The reason we have a ring is because we have lots of small grains, each of a slightly different orientation, and they're rotated, they're mismatched. If we let those grains grow, or actually have a single crystal, what's going to happen is, instead of having rings, we're going to have individual diffraction spots, okay? And you can see how these overlap very precisely with the various rings. Okay? So when we go from polycrystalline to single crystal, that's what we get, okay? The same principle holds for measuring the D spacing here. You've got the camera constant, you've got the wavelength, you measure the distance, you can tell you what the D spacing is for that particular reflection. Okay. So what do I have here? So how do you index simple diffraction patterns? What we do is we use the camera constant method. We make a table of diffraction spots, and from that table of D spacings, we can look up possible crystal structures. Now, why do I say make a table? Because it depends on what you're looking at. This is a collection of diffraction patterns, all from the same material. Okay? They're all from silicon. They're all from a camera length of 470 millimeters. Okay, but they all look different. And they all look different because this is a single crystal, and we're going down different crystallographic directions from, let's see now, that's a 110, that's a 100, that's a 111. What's this one? Let me look at it closely. 112. No, that's a 112. Now, you notice I'm looking at these, and I can almost index them just by looking at them, and I'm doing that by symmetry, okay? Because I know what this looks like. look at this. This looks like, okay, let's start here. That's a nice square. Silicon is an FCC. That's a cube looking down the 1, 0, 0 direction. This one, if you look at it, it's a hexagon. I'm looking down a 1, 1, 1 direction. I'm looking along a diagonal. This one is a squashed hexagon. Okay? That's a 1, 1, 0. Okay? Now, I can do that because I've been looking at these for years. Okay? We can nicely, if you want, measure the spacings using our camera link constant and make a table. And we said, these are the D spacings I see in this pattern. These are what I see here. These are what I see here. And then you can compare it to a table of numbers. So this would be a table of numbers that we can make and say what sort of HKL indices they are, what index they are, and whether we see a reflection or not. Using those, we can determine something like this. So here is, again, silicon. We've got a nice squashed hexagon now, right? You see the squashed hexagon? I can measure, let's see now, I think the next one shows me, yes. Let's do this, yeah. So I measure the distance between those two. I call it R1, R2, R3. I can measure those distances. I can look at the ratio of R1 to R3. I can then say which of these are allowed reflections. I'm going to go backwards now. We're looking at these, and some reflections are allowed, some are allowed, and some are not allowed, depending on the crystal structure, whether it's an FCC, a BCC, or diamond. Okay? And then from that, I can determine a ratio, and then from that, I can determine what the plane is. Now, I showed you that very quickly. The only way to do this is to sit down and do it one by one. Okay? But that principle is there. The other thing that happens is when I look at diffraction, I can relate diffraction patterns to crystallographic directions in the solid. So I'm looking at, for example, the cube zone, 001. How many of you know what a Wolf plot is? Did anybody know that? If you had any, who's had X-ray diffraction courses? Anybody? One. You know what a Wolf plot is, right? Okay. Think of the Wolf triangle, or the serigraphic triangle. This is the serigraphic triangle that you would see in normal diffraction. We go from 001 to 011 to 111, and we go along different reciprocal directions. We see the patterns changing very symmetrically. Okay, now that's a pretty complex structure. That's because this is not simple silicon, but rather an ordered PCC. The other thing to realize is that the diffraction pattern and the real space image are reciprocals to each other. Okay? When you're looking down a cube axis, it doesn't matter. If it's a cube, it's a cube. But when we look down the 011 axis, for example, the pattern is short this way and long this way, and it's the opposite in real space, because the diffraction pattern is reciprocal to real space. And here's the 111, always looks the same. It's always symmetric. You can cheat. You can look it up in a book. Okay? Or you can do it by eye. There's also a bevy of computer programs that'll calculate what diffraction patterns look like for you. Okay? I would, if I were you, I would learn what the diffraction patterns for your systems look like. If you're always working with FCC, learn what FCC patterns look like, BCC, orthorhombic, tetragonal, whatever it is. You should learn to recognize what the patterns are, because you'll be seeing them a lot. And it's a lot faster to be able to recognize and look, oh yeah, that's a 110 or that's a 111. And remember, the different crystal structures have different shape patterns. Now, in addition to a regular array of spots, when your sample has a finite thickness, you will see what I call regular diffuse scattering, and you will see a bevy of dark and bright lines going through your diffraction pattern. These dark and bright lines are called Kikuchi lines. After Kikuchi, the guy that first not discovered them, he described what they were. Okay? And these lines are elastic diffraction of inelastically scattered electrons. So what's happened is electrons comes in, it's lost energy, it's become inelastic, and then it diffracts. So what's happening is an instant electron beam comes in, it hits an atom and scatters, loses some energy. Some of it goes forward, some of it goes off at an angle. Those inelastically scattered electrons also hit the Bragg planes, and they get diffracted. The difference is they are tied to the crystal structure of the solid. And what will happen is, oh, you see it here. We have the dark and bright bands corresponding to whether it's a short diffraction or a long diffraction. White lines versus a dark line, okay? This is a very thick sample. It's so thick that we can't even see the Bragg reflections anymore. We can't see those bright spots. But the Kikuchi lines are still coming through because they're diffraction of inelastically scattered electrons. When it's very thick, you have a lot of inelastic scattering. When it's thinner, we have a combination of both. When the sample is very thin, you get no Kikuchi lines, you just get the Bragg reflections. These are very useful. They're very useful because for me, I use them as a roadmap. Okay? I'm going to show you now. This is a Kikuchi map. Okay? Something I created back in 1978. It's an experimental Kikuchi map. Each one of these squares is an individual diffraction pattern. So you see, I took a lot. I took my crystal and I started at 001 and I slowly tilted it and took a photograph of each thing. Why did I do that? Because now look at the map that I've produced. I can, using my Kikuchi bands, travel. Oh, I know I'm at 001 and I happen to want to know I want to do a crystallographic experiment and I want to go to the 111. I can look at this map. The spacing of the Kikuchi bands is proportional to the despacing of the lines you want. The direction is proportional to where you want to go. I want to go to 111. I can look at this pattern and say, oh yeah, I want to go that way. And I can just travel along that Kikuchi band all the way till I hit the 111. Or, if I don't want to go to the 111, but I want to go to the 112, the 113, the 114, I can go across that. Or I can go from 001 to 001 to 011, or I can go to 012, 013, 014. Now, who caught what I just did? I did simple vector math, okay? I know that's 001. I know that's 011. If I do a simple vector addition between those, I'm going to get that point. What's it going to be? That's 012. I'm going to vector math from this one plus this one. I'm going to get that. 013, 014. Similarly, we can go along here. From there to there, the first major one is 112. So that's 111 plus 011, 112, 113, 114. We can go vector math in here. Very simple way of indexing your pattern. More importantly, it's a roadmap of your crystal. You will, depending on the kind of question you're asking, need to go to different directions in reciprocal space or in crystallographic space to analyze an image. If you have a Kikuchi map in your pocket or on the wall or in your head, you can travel around reciprocal space to go to very specific directions in crystallography without spending a lot of time trying to figure out where you are. And again, that's an experimental one. People publish them too. And you'll notice that looks very much like what I just showed you. There's the 001, 011, 111, okay? This happens to be for an FCC system. They're again slightly different, BCC, HCP, whatever, okay. How did we do that? One of the things I didn't talk about when we talked about the microscope is the specimen stage. You put a sample in the microscope. How did you do that? You put it in some kind of a holder, some way of holding it and putting it in. Not only does that holder allow you to insert a sample into a vacuum system and move it around, X, Y, Z, it also allows you to do tilting, okay? There are a whole variety of different holders depending on which kind of microscope you have. Some Some holders are single tilt, only tilt one way. Some are double tilt, so they allow you to tilt one and then a second. Other ones do heating, cooling, or whatever. Because this is you've got the Thermo Fisher Titan downstairs, you have what's called a single tilt holder, so there's only one sample holder. There are some microscope manufacturers. This is from a these are JOL systems, I think. They have two holders. Most people just use one nowadays. It used to be, well, we'll load two so we can load two samples and look at two. Very few people do that anymore. All right, so we talked about apertures. Is that the right slide? Yes. We talked about apertures before, and we talked about apertures doing two things: controlling the beam current, controlling the coherence. But in diffraction space, they also control something else. They control the angle of the beam and the angle that we see in the diffraction pattern. So it's going to go back to our very first image that we had before, where I had the cigar-shaped guy. And if you notice this diffraction pattern, those diffraction spots aren't nice small pinpricks, they're disks. And the reason they are disks is because my beam was focused down onto the sample. In order to get pinpoint diffraction, we have to have a parallel beam of electrons hitting the sample. Okay? When that happens, in the back focal plane, the electrons are focused to spots, very, very small spots. If we have a convergent beam focused on the sample, those spots become disks. Okay? Typically, as soon as you see a disk, you say, it's still a diffraction pattern. We tend to call it a convergent beam diffraction pattern rather than a parallel. Why? Because the beam's converging. Very simple. Okay? How different can it be? Here is the same sample, same area of the sample, one with a near parallel beam, notice the small spots, and one with a convergent beam. All right, now let's look at these two because I want to think about it for a difference. So one's with a parallel beam, one's with a convergent beam. That's the parallel beam, that's a convergent beam. These two spots are these two spots. Okay? Where's that guy? Is it there? It's there, you just can't see it. Why? Because that intensity is now spread out into a very large disk. So it's very weak. If we did a really long exposure, we would see a large diffuse, in fact, a spot this big, roughly right here, okay? See that guy? Is that guy? Notice how big he is? Notice very, very interestingly, there's a lot of other information hidden in here, okay? Is that information here? Absolutely. We don't see it. Why? Because the intensity is so weak. So what is the advantage of convergent beam diffraction? A, you have a smaller beam. B, it reveals additional information about the solid. Look very closely at this diffraction spot. See all these lines in here? We'll talk about that, and Hamish is going to talk more about it when he gets here. Look very closely. Sorry, the exposure isn't right, but you can see some of this information just barely in there. It's actually all of this information here is here. We just can't see it because it's not illuminated. So how do we go between parallel illumination and convergent beam illumination? You do that all with your probe forming lenses. Okay? And remember, I told you about focusing your beam down on the sample, and then in order to get a more parallel beam, what do you have to do? You have to under-focus the beam. So you have to weaken the lens. So when it's focused here. When I weaken the lens, the focal point moves down. The more I weaken the lens, the more parallel the beam becomes. Okay? Remember that. And ideally, when it's as weak as possible, I have a parallel illumination of the sample. Now, there's another consequence of making the beam more parallel. It gets bigger. Okay? For a given aperture size, the aperture isn't shown here. For a given size aperture, the beam is a certain size. If I want to still have a parallel beam but have a smaller beam, what am I going to have to do? I have to put in a smaller aperture. When I put in a smaller aperture, what happens? The intensity drops, okay? All right. Select area diffraction is a methodology by which we can get a diffraction pattern from a certain area of the sample only. Okay? If I put a beam down on the sample and there are a lot of grains all over the place, I'm going to get diffractions from everything. Ideally, I would like diffraction only from one spot or one interesting area. How do I do that? Well, there's two ways of doing it. Today, most people just focus the beam down to a certain spot. That's actually probably the best way today on how to do it. Focus your beam down. Yes, you will get a partially convergent beam pattern, but you can still analyze it. In the past, we used a technique called select area diffraction. And in select area diffraction, what you had is you have a virtual aperture that's illuminating an area of your sample. Oops, no, now I've done it. Hang on. Which one do I push to get it back? This one? Nope, that's not it. That one? Nope. That one. Ah. Ideally, what we'd like is a nice parallel beam hitting, I keep touching the screen, hitting our sample. We can't put an aperture directly on top of the sample. Usually we want a very small area. So what we do is we actually put an aperture further down in the electron optical column, down in the lens stack, and that aperture projects backward to a small area on the sample. It gives us a limited diffraction pattern. Does it work? Yes. Has it been used routinely for years? Yes. The limitation is there's only a certain size area that you can define with that. Again, what causes that limit? Aberrations in the lenses. So can we insert an aperture and define an area on the sample from which to get a diffraction pattern? Yes. On a good day with the wind blowing right and the phase of the moon in the right quarter, you're getting half a micron or so. Okay. That might be good enough for your experiment, but it might not. Most of the time today's it's not. The alternative is just to focus the beam down. I have not done select area diffraction in decades. Okay? I've used focus probe, I've got a convergent beam pattern, and the modern microscopes, particularly those with corrected optics, can give you very small parallel beams, as small as 100 angstroms, and it still be parallel. So I don't need select area diffraction anymore. The instrument you have here is not a probe-corrected machine, but an image-corrected machine, but you'll still be able to get a small probe. I don't know exactly which lenses you have or how small you can get, but it depends on the lens, the number of lenses, and the sizes of the apertures. But certainly, 1,000 angstrom probe will be easily done on the machine here. All right, let's move forward. Yes, we got that already. All right. Why do I want to do convergent beam diffraction and not just always do select area diffraction? Well, I already mentioned this already. There is an aberration because of the aberrations of the post-specimen lenses. If you don't have an aberration corrector, there is a certain minimum area that you can see, and that's related to the angle of scattering that you get, the Bragg angle that you're looking at, and the aberration coefficient, CS of the lenses again. That defines what the minimum size you can see is. As a result, half a micron on a good day with the wind blowing right is about what you can get for select area diffraction. If that's good enough for you, select area diffraction is fine. There's nothing wrong with it. In the real world, nowadays, that's pretty big, half a micron. And we want to do, 1/10 of a micron or smaller. So what we want to do is instead of going with a parallel beam, we're going to focus our probe down. And here we have the advantage of controlling forgetting about overfocus regime now. We're either going to have a focus probe or an underfocus probe. Okay? The more you underfocus the probe, the more parallel, the smaller that angle gets. So you can get near parallel illumination or close to it with a probe forming system. So select area aperture isn't really too keen. Okay? Another example, we've seen this one several times, but now what I'm showing you is an example of going from same system now. All I'm doing is changing the focus of the lens. I'm going from near parallel illumination, to slightly convergent, 10 to the minus 3, to 10 to the minus 2, 1.6 times 10 to the minus 2 to 2.6 to the minus 2. Notice how these disks are getting bigger. Remember those very weak spots that we saw before? You can see them here, where I'm just starting to spread them out, okay? And at this point, they're no longer visible, okay? We see some distortion here. That's probably because I haven't focused things, okay? Nicely. One of the things that Hamish is going to talk about when he gets here, which I expect soon. Is he on his way? Yeah. Good, because I'm getting tired of talking. Yeah. Well, we just have a little bit more, and then we'll stop, I think. Let's see, how many? I think we have a little bit more. Well, let's see. We've only gone for an hour. We can go a little bit longer. But I'll need to stop talking a little bit. Hamish will be talking about the information in convergent beam patterns, okay? This is a beautiful convergent beam pattern from M23C6. Notice what's very important in this pattern, and again, Hamish will talk to you. We have some reflections that are very dim and almost blank, other ones that are fully excited, some that are in between. We can look at complex. This is now all silicon. There's a nice parallel pattern. And now I'm going to go to convergent beam mode, and that pattern becomes that pattern. And now all I'm going to do is I'm going to keep my convergent beams fixed. I'm going to change the thickness of the crystal. So all I'm going to do is move the probe to a thicker area. I go from this to this to this to this. Do you see the pattern here? Okay? You see the structure of this changing? What does that tell you? If I know that periodic change and I can measure it, I can measure the thickness of my sample. Power of convergent beam diffraction. Not only do I get the d-spacing, I can also measure thickness of the sample. This information, by the way, for those of you that are really interested, if you're interested in the physics of electron scattering, you can measure the structure factor of the solid. The other thing Hamish will tell you a bit about is high-order Laue zones, high-order scattering. If I look just in the 0, 0, 0 disk, the straight-through beam, and the sample's relatively thick, you see a lot of structure in there. That's very important crystallographic information. It gives you information about the 3D structure. It also is very useful for very accurately aligning my sample. I'm right on the 111 zone axis right now. I can tell that thing is centered as close as I can get by. This is just slightly off. That distance is tenths of a milliradian, okay? Because remember, a typical Bragg angle, this is about 5 milliradians. You notice, so that's 5, that's probably, that's 5, that's 2.5, that's 2, that's 1, so we're a few tenths of a milliradian. So very accurate alignments. When we start talking about inelastic scattering tomorrow, we'll talk about the inelastic scattering. And remember we said the beam's coming in, it's interacting with sample. Most of the stuff we talked about is elastic scattering. Well, what you don't know is that, go backwards here, when I have this pattern and I just put my sample in the microscope, we've got the elastic scattering, but also on top of it is all the inelastic scattering. Kikuchi lines, remember those? They're inelastic scattering. They're sitting in here. Now, if I have something called an energy filter, I can remove the inelastic scattering and then just look at the pure elastic scattering, okay? You can see what happens is we get rid of all the diffuse background here. That again gives us more information about the solid. There's actually information here and also valuable information here. I mentioned that structure in the diffraction and convergent beam patterns is very interesting, okay? If I look very closely at this, this is now a diffraction pattern where I only have 2 reflections excited. Notice the periodicity in those lines. I can show you that periodicity, mathematically, is due to a change in the thickness of the solid. If I take a line scan through here, this is what I see. If I measure the periodicity of those fringes, and I know the material that I'm looking at, and I know the lattice parameter, I can tell you how thick that sample is. Okay? There's a methodology called, what's it called? Sorry. Oh, I've forgotten the name. Sorry. Back up. Okay. Pat Kelly developed it. Let me back up. Sorry, I have to back up. What he's been able to show is we can look at a diffraction pattern. We can look at the 0, beam and a diffracted beam. I know what that diffracting vector is. As the sample thickness changes, I go from a very thin sample to a very thick sample. The number of fringes that are here increases. The more fringes I have, the thicker the sample. So if I measure the number of fringes and their periodicity, I can measure the thickness of the crystalline area of the sample. Okay, there's the mathematics for it and the references for it are all here. Basically what you do is, we do a line scan through our diffraction pattern. We measure the fringe spacing. We do a plot of the deviation parameter as a function of 1 over z squared. We get a straight line. The slope of the line tells us the thickness. The slope of the line tells us the extinction distance, and the intercept tells us the thickness. Okay. There's still yet a third method on doing convergent beam diffraction. It's called packbed, positioned average convergent beam electron diffraction. And what you do here is you have a very small beam and you scan it and get an average diffraction pattern. You scan it over a small area. You get a certain thickness. You go to a different area and you look at the patterns as we go to different areas. They get thicker and thicker. We then, knowing the crystal structure, do a model of that. And from the model, you can tell the sample thickness again. So here's, for example, a experiment and a simulation. Experiment and a simulation, they can see they match. Now, what's good about measuring sample thickness with convergent beam patterns? Only works for crystalline materials. So if you have an amorphous sample, can you measure the thickness with convergent beam diffraction? No. Okay. There are other tricks you can use. We'll talk about them later. So, but what happens if you have a crystalline area with an amorphous layer on top and bottom? You still measure the thickness of the crystalline area, but remember you've got amorphous material on top and bottom. So what's the question you're asking? Is the question how thick is the crystalline area or how thick is the total sample? Those are two different questions. So, all right, I think we're about to the end and I'm getting talked out. That's the same. Oh, okay. Other stuff that Hamish is going to talk about, and I know it because I've seen his slides already. We looked at them over a few beers last night to make sure. He's going to talk a bit about higher order Laue zones, more information that you're going to get. So just give you a preview of what that is. Up to now, we've been just talking about diffraction right around the 0 beam. If you drop your camera length way down, we see diffraction very far out in reciprocal space. Hamish will tell you a bit about that. Higher order Laue zones, I don't want to get his thunder, take away from it. But he'll tell you all about this. He'll also tell you about the symmetry that's possible in here. I'll give you a preview of this. We look at this diffraction pattern, and what do we see? What kind of symmetry do we see? I didn't hear somebody louder, I can't hear. 6, 3, who's picking 6, who's picking 3? Who's saying neither of those? What did you? 3, wrong. 6, wrong. I want you, if you look at this, it looks like either 3 or 6. And in fact, if you look at the triangle, you say, oh, it looks like 3. Let's look very closely at that inner circle. Look very closely at that inner circle, and this is what Hamish is going to talk about. This is the blow up in the center of that. I want you to look very closely. Is that threefold symmetric? The answer is no. Okay? Now, could you have seen it from this pattern? Nope. Can you see it from this? Not quite. But we can see it here in the higher order Laue zones that are in the 0, 0. You see a mirror plane right here. It's twofold symmetric. Okay? Close to threefold. And what's happening here? we've got a distortion of the lattice, just slightly. If it was perfectly symmetric, this axis would look see these two? This one would look exactly like these two. So it's a very slight distortion, so very small changes in lattice parameters can be detected using this technique. And again, I'm going to leave that to Hamish because I'm getting tired of talking. Let's see. We can also use these Holtz lines to actually measure the accelerating voltage of the microscope. You turn a number and you say, oh, I want 300 kV, and you say, oh, it's 300 kV. No. It probably on most microscopes might be, instead of 300 kV, 298. Okay? And there's a reason for that because of the way they design some of the optics, and they design the systems to be compatible with electron loss spectroscopy. In the past, it used to be approximately 300 kV. Now it's 298 because they need 2 kV to do something else. But the very nice thing about these higher orders of Laue zone slides, and this one is threefold symmetric, by the way. You notice this one is perfectly symmetric. You notice how these Holtz lines cross. If I change the accelerating voltage a little bit, I go from 113 to 100. And on some microscopes, you can tune the voltage very easily. You see how those lines change spacing, okay? So if you really need accurate measurements of your accelerating voltage, can you do it? Put in a known material, a known crystal. This happens to be silicon. We know what silicon is. We know the crystal structure of silicon. We can calculate this, and we can then match the accelerating voltage and determine exactly what it is. That's how I knew this was 113, by the way. We knew this was 100. We did the calculations. We got a pattern where these guys all collapse to a spot. And knowing that it's silicon, knowing the zone that we're in, we're able to say, this is 113 kV, pretty precisely. All right, I think I'd like to end on, I think this is my last slide. Yes, it is. That's good. I can't talk anymore today. There's one of my very pet peeves. You know, pet peeve in the US is something that really gets me annoyed. The thing that gets me annoyed is a person will go up to an electron microscope and take a high resolution image. Okay, here's a high resolution image. We can see an image of a periodic image here. Very great. Then they will take a Fourier transform of that image and put this up and say, there's my diffraction pattern. A Fourier transform is not a diffraction pattern. Okay? Very important to remember that. A Fourier transform represents the periodicity that you see in an image. It's not crystallography. Is it related to the crystallography? Well, if the periodicity in your image is related to the crystal structure, yeah, it'll be related, but it's not a diffraction pattern. If you're missing, for example, you're out of focus or something, some of these diffraction spots, periodic images, will disappear. Okay? I've seen people try to do an image like this, then take this and say, well, I'm going to measure the lattice parameter of all my spots now. And they make a measurement on a Fourier transform. And all they're doing is measuring the periodicity of the image. So Fourier transforms are very useful tools. You saw how I use them to look at the astigmatism, because they show me the symmetry, the asymmetry. I showed you how the Fourier transform can tell you when the sample's drifting, if there's a distortion. Really powerful tools. They're very useful. Use them, but use them properly. All right, I'm done talking for today. I'm talked out. I need to let my voice take a break. So I think this is a good time to take a break, and I expect Hamish to be arriving shortly. Good. All right. Time for questions and a break, and a bio break, and whatever we're going to call it. Cheers. Yeah, I went for an hour and a half. That's good.
So we can have a tea. I'll come back at 4. What about you? Want to have something?
I know. I need to dry. I need just to be quiet for an hour. No, I've got actually I found in my bag.
Okay.
Throat lozenges. This is what I need.
Okay.
Oh.
Okay. I'm very happy to be here and to introduce Professor Hamish. He's a world-renowned scholar and professor. He doesn't require an introduction, actually. But at least I want to tell you his association with IIT Madras. That is something you may not be knowing. So ever since we started establishing the Electron Microscopy Center at IIT Madras, Professor Hamish was there in the very first place in 2010 onwards. And he has been the he's on the International Advisory Board. And ever since we started discussing, and I mean, he helped every aspects, and I keep taking advices from him, right from the, preparing the rooms and other things, so on. And then after that, it is only growing. Every year our association get closer and closer. We are immensely get benefited from that. And you may not be knowing that even this workshop is completely organized. I mean, organized by him, I would say. Dr. Nestor is first PhD student of Professor Hamish. Okay, so that's the kind of he has clearly organized this with this connections and so on. And we are really enjoying Dr. Nestor's lectures. And we are really fortunate and happy. And talk about biography of Professor Hamish. All of you would have seen this in his web page. Very nice biography he has given. But I will not read everything, but at least few of them. He obtained his PhD in 1972 from University of Birmingham. And after that, he joined Ohio State as an Ohio Regent Eminent Scholar and Professor. And he has been the visiting professor and scientist almost several universities around the world. And one of the important thing is he is also senior Humboldt researcher at University of Göttingen and senior visitor at University of Cambridge, visiting professor at University of Liverpool and Max Planck Institute, Stuttgart. And he has been recognized with several prestigious international awards. The list is quite big. I don't want to take that time. And he also serves as a director of the Center for the Accelerated Maturation of Materials at OSU. And he has been the member of National Materials Advisory Board and the US Air Force Scientific Advisory Board. He has consulted for a number of national laboratories and several industrial companies. He's a fellow of TMS, ASM, IOM, MSA, and MAS. He has published over 430 papers in scholarly journals and given 370 invited presentations. He has graduated over 52 doctoral students and 36 students graduating with the degree of MS. So friends, so it's our honor that Professor Hamish is giving this workshops, and Professor Hamish, the floor is yours.
Thank you. And of course, the organization of this workshop is Professor Sankaran and Sudhakar, wherever he, yeah, there he is, yeah. And Nestor and I are here just as the talkers. In fact, my job was to make sure that Nestor came. And I thought that meant he was going to give all the lectures. And then a few months ago, I get this email from Sankaran saying, Nestor will give these lectures, and then Hamish will give these lectures. And I was like, oh. Said, he's a good negotiator. He just completely keeps silent until the last moment, and then you can't say no. It's a clever idea. I must remember that in the future. So. Okay, so today I'm going to talk about convergent beam electron diffraction. I was visiting one of your prestigious hospitals this morning, just checking them out, making sure that they were in good condition. And we can take these images and so on, these diffraction patterns, just in a second or so or less, right? Whereas I had to lie flat in this stupid machine with it banging away my ear for about an hour without moving. And you can imagine Hamish at my age without moving. Crazy. And I was so scared to move because if you move, they start again. And the banging goes on, right? And these stupid magnets they have. However, here I am. And then you get 2 more lectures from me tomorrow. One on the dynamical theory, which is chosen because I know nothing about it, and then on diffraction contrast, which I used to know when they allowed me near the microscopes. I'm not allowed there anymore. I think it's shaky hands that, no, it's not. I just think I'm just too old for it. So, however, let's have some fun with convergent beam electron diffraction. So this was thought about by a number of people. This is before you guys were born. This was back in when I was at Illinois days, my first 17 years at University of Illinois in Champaign-Urbana. And that's where Nestor came to be my first grad student. And I would say about in the 80s, John Steedes' group in Bristol had sort of pushed convergent beam electron diffraction. And 99% of the electron microscopy community avoided it because every explanation from the John Steedes group, which is he was in physics at Bristol, every explanation was so contorted and complicated that we were like, we have no chance to understand how to use this technique. And we got going, spoils the picture, sorry. We got going with the trying to get into this technique and found out that it was delightfully simple. So, I hope you will agree after I give a talk. So, you know that most of our imaging in the electron microscope is done with a parallel beam or nearly parallel beam. And then we do things like we have simple pictures of Bragg's law and a diffracted beam going here and the forward beam going straight ahead. And of course, if you really get crazy in your microscope, you can cause the beam to be sort of focused down, so it's like a cone intersecting the surface of the foil. And so now we have a range of incident beams, if you like, right? So you might think, well, that really spoils things, but actually opens up a lot of opportunities, and I'll show you this. First of all, this is a diffraction pattern taken in a very thin, can you see? Yes, you can. A thin part of the foil. So all we have is sort of these bright discs here, and sort of dark background. And you might think, well, what information does that give us? Well, we'll see. But think about discs. So if I'm a disc like this, and the beam's coming down, right, and then forming this diffraction pattern, that disc, basically the unit of travel across that disc is angle, right? Because it's talking about, you know, going from the direct beam across to some diffracted beam and so on, so it's angle. So it means that there's obviously a range of angles going across this disc here, or that disc there, or that disc there, and that is precisely the angle of the convergence. It's like we've got a bunch of beams there, right? Okay, so here's a better bit. We go to a thicker part of the foil, and we start picking up all sorts of information now in these discs. And that's going to be the interesting thing for us to look at, is what's happening with these discs. All right, so let's go back to something you know about, the Evol sphere construction. Right, so we know what that is. And you also know that your professors have told you that if you want to predict what a diffraction pattern looks like, you just say, I'll take a plane section perpendicular to the beam, and wherever that plane section intersects the lattice, we'll get a Bragg event. So because we have a range of angles, it's as though we have a whole bunch of Evol spheres here. And so the extreme part of the Evol sphere, when it's over, say here, and then it'll go over there to the extreme part, and of course it does that around 360 degrees. So, for example, this Evol sphere might intersect that disk out here in what we call the first order Lowry zone, and that means we've established a Bragg condition there, and we'll get diffraction. Okay. Normally, what we think about is just doing a plane section perpendicular to this with our Evol sphere. So this is an exaggeration here, and then the other extreme will be, say, down here, and then we'll get some other. Oops, there's another intersection up there. Another Bragg condition is fulfilled, and so on. And so you can think of it. If you're really bright, you'll think of it as a bunch of Evol spheres, right? But if you're a metallurgist like me and not very clever, you'll think of it, oh, let's think about it with disks, right? And one Evol sphere, and then we'll have disks. And wherever that Evol sphere intersects the disk, in any part of the disk, we've established the Bragg condition again. All right? So you're still thinking, why are we bothering? And that's a good thing to think about. Why are we bothering? All right, so at the same time that this technique was starting to be introduced, at the same time, the electron microscope manufacturers did a wonderful thing. They allowed us to view more of the diffraction events. So you could go out, normally we would see this in the old days. When I was a grad student, we'd just see that part of the diffraction pattern, and that's all you'd see on the screen. We didn't even know there was a thing called the first order Lowry zone or the second order Lowry zone, right? And so this is the intersection of the eval spheres, or let's say we've got one eval sphere and these are disks, little disks out here. All these are Bragg conditions satisfied in the first order Lowry zone out here. And if you can just see it, can we turn these front lights off at least? Is that possible? Over here? Oh my gosh, there are too many buttons to press. I'll turn it on. Great, thanks. You can see why I'm not allowed near the microscopes anymore. I can't turn lights on and off, let alone a microscope. All right. And so, right, so going back to here, right, this is called the zero order Lowry zone. And normally in the old days we'd see events around here, diffracting events around near the direct beam. This is the next one up, the first order Lowry zone, full of reciprocal lattice points here, because of course we are talking about a 3D crystal. And this we call the second order Lowry zone and so on. So, and there's a manifestation of what we're seeing. And the reason we can see it is because the manufacturers allowed us to go out and look at further out than just here. So, and if we'd not been able to do that, this technique would never have really taken off. We have to be able to see out to these higher order events out here. And it's just Bragg diffraction still. Nothing really funny about this, nothing special yet. Okay. And this now says, okay, if we're thinking about our diffraction points as being now these disks, then this is the extremities of the eval sphere. If we're thinking about that in terms of the angle of the convergence. And this is what we're going to see in the diffraction pattern. Okay. So, when we have an event out here, it means we've satisfied Bragg's law, and we're going to get diffraction. So where does the intensity come from that gets to here? Where does it come from? It comes from the direct beam. All right? So you're diffracting, you're taking that intensity and you're putting it out on that first, say in this case, the first order Lowry zone. And this is a long distance here, a large angle, and so that scattering is going to be kinematical. And it's simply going to be, I'm taking those electrons, and I'm plunking them out here by diffraction. Okay, so well, there's something that happens because of that. Am I going backwards here? No, I'm going forwards. Good, Steve. All right, so these are zero order, first order, and second order Lowry zones. And here is, say, my disk out in the higher order Lowry zone. It could be first order, second order, whatever. Oh, will there always be a first order Lowry zone? Will there always be a second order Lowry zone? Well, that depends on the structure factor, right? Which is another, we have Bragg's law that tells us about diffraction, and then we have the structure factor that tells us about intensity in that's diffracted. So you have to worry about that. But let's say we're not worried about that in this case. You have a first order, second order, and so on. So one of them, the high order Lowry zone lines. I'm going to get intensity when the eval sphere cuts through this disk here, and that's going to be taken from the direct beam, from the disk in the middle. So if we're taking out this intensity and plunking it out here, it means we've got a deficiency in intensity in the disk, exactly like this. All right. So this is the intersection there. Let's say the eval sphere intersects over here. We know that in principle, if it was a parallel beam, it has to intersect right through the reciprocal lattice point almost, because we've got a thin foil effect as well, but let's not think about that yet. But when we have disks, we can have diffraction from anywhere in this disk. So here it's on that side. It might be over on this side. But you're going to pick up these in the high order Lowry zones. You're going to pick up these bright intensities from the diffraction event, kinematical diffraction, and it's going to leave behind a dark line in the zero order disk. Now that's tasty, because that means that's information in the zero order Lowry disk there, that central disk, that's going to reflect all these different diffraction events in the higher order Lowry zones. Kind of interesting. So we're going to end up in our bright field disk here. Let's call it the bright field disk. It's the one in the middle of the diffraction pattern in the zero order Lowry zone. And we're going to end up with these lines here. And they are all dark because it's deficient intensity, because we have taken those electrons and put them out to some disk in the first order or second order or third order Lowry zone. Okay, now, so you might say, well, so what? And you can see they've got all these weird kind of indices that you don't normally pick up in a normal SAD diffraction pattern. But this is going to tell us something about the symmetry of the crystal. So these are really important lines here. And we call those Holtz lines. So they're higher order Lowry zone lines. And they're dark lines in the bright field disk. And of course, there'll be above background bright lines in the Holtz disks. Okay, so what kind of symmetries do we pick up then in our seabed pattern? So we're taking a look here at the bright field disk here, which we've magnified, and you can see it's got these lines in it, the Holtz lines. And we've got, in this case, the first order Lowry zone out here. And that's all we're picking up in this particular pattern. And there's some other things here. These are the Kikuchi lines that you should know about. Okay, so there's a lot of different things here, and we call these the whole pattern symmetry, the zero order, and the symmetry that it exhibits. That's the disk here. And then we have a projection diffraction symmetry, which will be the symmetry of the zero order Lowry zone here around the central beam. Each of those will give us information, as we'll see when we start talking about applying this technique. And let me show you a bright view of a large view of the, let's say, a Holtz reflection, sorry, a bright field reflection, the one right in the middle of the pattern. Here all our lines. And as I told you, would be where we've had a diffraction event in the high order Lowry zone. It's dark because we've taken those electrons and put them out there in the zone. So what's funny about this? What's funny about this picture? See a bunch of straight lines like this, right? What else do you see? Well, we see these very naughty lines here. Look at this one here, curved. And this one curved. And that's curved. And that's curved. And that's curved. And that's curved. And the distance between the lines, in those curved lines incidentally, varies from that being the thinnest to the next thickest to the thickest of all of these pairs. So where are they coming from? Well, they're just a result of dynamical scattering. So in fact, the Holtz line would be something like this down here, connecting onto this here, and that on this line here, and coming over here. But what happens is that what happens is that they dynamically split into these lines here and here. So we don't have to be scared of those. The fact that they're different distances apart tells us that there's something going on with the symmetry of this particular sample. So it's actually nice information for us. But we can simulate where these lines should be if we know what the structure is, and we can plot out what they would be. And these guys doing a kinematical calculation, which is what we normally do, would just be straight lines. And if you did a dynamical calculation, then you'd end up with this splitting. So that's the bright field symmetry. And within that, there can be this, not always, but there can be this dynamic splitting. Okay. And then this is our projection diffraction symmetry, which will be, there's the bright field disk. And then we have this information in these reflections out here. These are the closest ones to that bright field disk. And so let's do two things. What's the symmetry exhibited by these guys? How would you define that symmetry? Well, clearly there's a six-fold rotation, right? Because I can rotate this 6 times around and it lines up each time. And then, if I take this axis here, then I have a mirror. That would mirror to there, and that would mirror to there, so on. So I have one mirror. And then if I have an axis here, you can see I have another mirror. Those two will mirror over to those two. So I have 2 separate mirrors, and I have a 6-fold rotation. So that's 6 mm would be the rotational symmetry here. And we're going to see, by using the diffraction tables, that will give us information. Yep.
How you would understand it is perpendicular mirror or parallel like mirror in 6-fold?
Well, say I don't have to understand why that's happening at the present time. I'm just trying to see what are the symmetries that I can see. And so if I put a axis here, I said I'm going to get these guys will mirror over here and they will mirror over here. Okay, so that's one mirror. I'd get the same mirror if I had that as the axis. I get the same mirror if I have that as the axis. So I only have one mirror there from that, one independent mirror. But if I have this as the axis, then these guys will mirror here, those guys will mirror there, and those guys will mirror there. And I get the same answer if I have that as the axis, the same if I have that as the axis. So that's another independent mirror. So I have 6 mm, it will be my symmetry for this. We'll see later on, very shortly, how we use that information. Okay, how about some other information? There are all sorts of things that you can see in these things. Do you see here these, what look like crosses? There and there. So they're kind of interesting because, in fact, really what's information here, the information is this line, this black line here. So it's absence of intensity, and we call that dynamical absence. So we're going to be showing that they're very valuable things to note in the diffraction pattern and help us really say something about the crystal. What they show is kinematically forbidden reflections. And that's the information we need when we go from point group to space group. And so this reflection here is kinematically forbidden. It's dynamically present because of the dynamical theory, but kinematically it's forbidden. So that helps us then define things, right? So, okay. So what it tells us is that it's kinematically forbidden, but it means that it's either due to a screw axis along the systematic row that contains those dynamic absences, so a screw axis along here, or a glide plane perpendicular. So a glide plane along here perpendicular with its normal going out this way. So it contains the glide plane and the normal to the glide planes out here. So we have information about glide planes and screw axes, and as I say, we're going to need that information when we go from point group to space group. Now this is going to be very simple because I'm a metallurgist, so it can't be complicated. So no one starts getting concerned. So what's interesting, if I was giving this as part of my course in Columbus, I would teach about crystal structure, point and space groups, determination of course, local lattice parameter determination. We'd go and take a peek at the dispersion surface, which physicists try and hide from us because they're very naughty people, Sudhakar. But we could take a peek at that. And of course we can simulate seabed information, and we can determine specimen thickness as well. So what we're going to talk about today is just these two, the first two. All right, so let's talk about phase ID and determining the crystal structure and so forth. What's the problem with we know that we can take a material, we'll grind it up, we'll shove it into an XRD, turn on the X-rays, get the fraction events, and we'll say, from that we'll determine what the crystal structure is, right? So why can't we take our electron beam, plonk it on our thin foil, look at the diffraction pattern and say, we can determine the crystal structure? The reason we can't do that is because even by just altering the thickness of your foil, you're changing intensities. And if you deviate at all in terms of orientation, you change your intensities. And so crystal structure determination in the electron microscope is a very difficult thing for us to do if we wanted just to Bragg diffraction a la XRD. I didn't say to you to do anything. So, excuse me, we'd like to have another way that we can do that. So XRD, you're measuring intensities, and from intensities you're going to crystal structure. What we're going to do in seabed is look at the symmetries and go from symmetry to crystal structure. So we're not going to worry about intensities too much, right? I just told you about dynamical absences, so we are going to use it a little bit, right? But that's when we get towards the end of determining things. However, all of this was happening, as I told you, in the 80s, which is a very long time ago. So today, if you go to Sankaran Center and you see the biggest microscope you can see and start using it, you'll do high-res imaging in it. And of course, all of you, well, first thing you'll think about is, I got to do a high-resolution image. My students are the same. So we were doing, you've all heard of high-entropy alloys by now. So this was a high-entropy alloy that we were working on, and it had this black phase. This is what we were interested in, everything happening in here. But here's this naughty black phase that was, we believed, was the cause of our brittleness of our high-entropy alloy. So we want to know what it is. We want to know what its composition is so we can adjust our composition and try and get away from it. And we'd like to know, of course, we'd like to know, I want just one of you. There we go. We'd like to know what's its crystal structure. So my student, Jake Jensen, immediately went and recorded a down zone axis HADAF image. And he brought it to me and he said, I'm having a problem because I don't know what this means in terms of the crystal structure. I've got these rings of atoms here, atom columns here, and these bright ones out here. And I said, maybe I should take another zone axis. So to try and simplify things, he got the next one, which is about as far away from understanding what the crystal structure is, right? So completely useless, right? And this third zone axis looked more like a normal HADAF image, but didn't tell you anything about the crystal structure. So he was in my office and I said, Jake, there's a thing called diffraction, rather than just imaging all the time. And I said, there's a thing called seabed. It can really be, you could use seabed on this and deduce the structure. And in his case, the space group was determined by seabed, and there's the, from the space group that he had, and lattice parameters and so on, into Crystal Maker. That's the model looking down the 0001 reflection. That, if you remember, is what he saw. And you can see it's a perfect fit. But what's important is, from those two seabed patterns, he determined the space group. In the good old days of John Steeves and his group, they said you can always get crystal structure in with one zone axis, which is complete nonsense. It usually takes a number of zone axes to get them. This was lucky, it was two. But then I know there is a God, because then Jake said, my goodness me, look at that. Just two diffraction patterns and you get the space group. I said, it's a very, very good technique. But people hardly ever use it these days, right? That's why I'm talking about it today, because it is so useful. So that worked really well. So I'm hoping you're thinking, okay, it might be worth listening to. If you get the, if you use what Nestor's going to talk about in the next couple of days, the XEDS, you can get the sort of idea of what the composition is. And this turned out to be an alloyed form of ZR5AL4. Okay, so crystal structure, point and space group. So we're going to make use of the symmetries exhibited by the patterns. That's the experimental part. And then we're going to make use of the tools from the crystallographic tables. So we're just going to have, it's like having a set of log tables. You won't know about log tables, of course, because you haven't seen them. It's all now in the little handheld computers. But in our day, we used to have log tables that we do our mathematics with. All right, so this is like having a set of tools that we've taken from the crystallographic tables and a bunch of measurements of what are the symmetries exhibited by the thing. So the tools, the tables look like this, our tools look like this. They're things like what symmetries of high order information do we see? The whole pattern and the zero order disk. So the projection diffraction is only two-dimensional, but the stuff in the zero order, the bright field disk is three-dimensional because it's coming from scattering out in the higher order Lowry zones. And then the stuff on the outside is obviously three-dimensional because it's coming from the higher order Lowry zones. So this is the information that we're going to see, this kind of information. It's going to tell us something about the possible diffraction groups. And then we take that information then, possible diffraction groups, they're the symmetries we've seen in the high orders, and get the projection diffraction group. And then we can go to tables like this that you can hardly read at the back there, I'm sure. But it relates the point group to the information we're seeing, the diffraction groups in these various orientations. Or we can go to this one here and say, okay, I've got a diffraction group of 2 mm1r, then the possible point groups are here and so on, down that row. So there are 5 of them for that particular diffraction group. And so you obviously need another one, and then you can narrow it down, and usually, and Bob's your uncle. And then, of course, there's this set of information from the crystallographic tables that we'll sometimes use as well. So there's a bunch of tools that you can use, and we'll get to that. So here's the example we're going to do, which is obviously one that was done in my group. That's why I got all the information about it. But it shows you that it's not a totally simple thing like the Bristol group would say, take one pattern like this and you've got the crystal structure. But you can get to it by using the symmetries that you observe and the tables that I've just shown you. So these are the symmetries that we're going to see in 3 different zone axes. This is the first one. It turns out it will be the 100 for the crystal structure we determine. But that's an after the event bit of information. But this is the first zone axis that we looked at. And you can see we have the information here in the bright field disk. We have the information here in the first order Lowry zone. And we have our projection symmetry here. And incidentally, oops, so that's where that came from. So it's got a dynamic absence. So that's very rich. So we'll see what those are. They are, we have a mirror here. So everything is mirrored across this. We have a mirror here, so everything's mirrored that way. And we have a mirror here, and we have a mirror here. And of course, in this pattern here was the high order stuff, is a mirror and a mirror. Okay. So this is the next zone axis. And in this particular case, we have mirrors again, 2 mm here, a mirror there, and a mirror here, and a twofold rotation. And the same thing here in the projection diffraction symmetry. We didn't get much in the way of high order Lowry zones there. So that was what turned out to be the 010, and then the 001 looked like this, and where we have, again, mirrors there and here, twofold rotations there, and a mirror here, across there, and a mirror here. So we have a mirror there and a mirror there. So if we take all that information and we put it here, we'll see for this zone axis we had 2 mm for the projection diffraction symmetry. The bright field symmetry was 2 mm, and the whole pattern symmetry was 2 mm. So these are the 3-dimensional informations here. So that from the tables, That tells us that this can be a 2mm1R or a 2mm. Likewise here, we had for the 010, we had 2mm. We had nothing in the bright field disk there. We had 2mm in the whole pattern. So that can be 2mm1R or 2mm, okay? And then for 001, we had 2mm and 2mm in those two. So they're all then the same possible diffraction groups. So we take that information and we say, okay, for the 100 zone axis, we had here either 2mm1R or 2mm. And then we look down here at the possible point groups here, and we noticed that there were no other higher order converging ring patterns were observed. So we can exclude the tetragonal, the trigonal, hexagonal, and cubic point groups. Otherwise, we'd have more information from our patterns. And so we're just looking at these two as a possibility here. Either the point group's going to be MMM or it's going to be MM2 from this one pattern. Okay, so from the tools, only MM2 and MMM point groups can give rise to the diffraction groups 2MM1R or 2MM. And what turns out, only MMM can give these diffraction groups to 3 different orthogonal zone axes, which is what we had from our information. So, I boxed in this one down here. So this is then the MMM, here's the MM2, and then the only point group here that has the 2MM1R, there is that point group. And so we conclude that that's an MMM is the point group. So you haven't done much work. You've just taken 3 different zone axes and then deduced from the symmetries you observed and the tables, you deduced the point group. However, unlike physicists and mechanical engineers, we, metallurgists, want to check. So say, is there a way we can check this? So we looked at another zone axis. We took the 110. Here's the 110. Oh. And so there's a mirror here. And incidentally, if you notice that here, out there's a little dynamical absence out there in that first order Lowry zone. So then we look here at this. So experimentally given patterns, here's our 110 down here that we just looked at. 2mm is the projection diffraction symmetry, and bright field was M, whole pattern was M, so 2R MMR will be our deduced diffraction group. And we look now, comparing these two here, and we see, oops, sorry, we see these are the possibilities that we have then, and we think that the point group is MMM here, and we notice that the 2MM1R includes the MMM, and so we point out that projection diffraction symmetry and then the whole pattern here, and oh, there we are with our MMM. So we've not only deduced that it's MMM, we've checked with another zone axis consistent with MMM and only MMM. And when we cut out all those higher order crystal structures, all the hexagonal, tetragonal, and cubic, because we didn't see any patterns that had that kind of higher order information. And so the next thing then is we say, we know it's MMM point group, now let's get the space group. So we know that's going to involve things like these dynamical absences. So by projecting the first order Lowry zone reflections onto the 0 order layer, it can be seen the reflections overlap, hence the unit cell is primitive. Right, so we're taking the points out here on the high order Lowry zone, say the first order Lowry zone, we're projecting where they are on this 0 plane here, and if they line up, we know that we have a primitive structure. If they go into the face center positions, we know we have a body center cubic. Remember, diffraction is the opposite way around. And if they go into the face center positions, then we know we have a BCC. So in this particular case, it's primitive. So that's the first thing we have towards our space group. We know what this unit cell looks like. Right? It's a primitive cell. And then we say, obviously if the reflection is projected onto body center positions, the real lattice unit cell would be face centered and vice versa. So we know that. So that was fairly simple. So by projecting the first order, that's that it's primitive. I repeated that there for some reason. All right. So the space group then is most readily determined by consideration of the dynamic absences. So where do we see those? So for orthorhombic systems, MMM is an orthorhombic point group. So for orthorhombic systems, we only have 100 glide planes or 100 two-fold screw axes. Right, so now we need to find out whether we have some screw axes or whether we have a glide plane. And the best thing to do there is to find out where are these dynamic absences, because then we can either say they lie on a screw axis direction or a glide plane whose normal will be to both the beam direction and that direction that contains the dynamic absence. All right. So we look for dynamic absences to reveal the presence of these symmetry elements. And let's take a look at the 110 convergent beam pattern. Did I say that? The 110 type. Okay. Must be effect of the my head being banged by that magnet this morning. Okay, so let's take 101. And the question is, do we see any dynamic absences in 101? Can you see any? I'll give you a clue. I'm going to head up here. Oh! There's one right there. And I'm going to go the other way. There it is. Okay. So we picked it up. We note the dynamic absence. And what it is in the OKO reflections. Okay. So there and there. So these are either due to a screw axis along here or a glide plane that runs through those dynamic absences. So it's either due to an 010 screw axis. That's possible. How do we know it's possible? Because we said these screw axes are possible. Or a bar 101 or a 101 type glide plane, which is not possible because we can only have 100 glide planes. So we know, this is not hard work, and it's a lot of fun because we're finding out a lot of things just by taking a few diffraction patterns. So we know that these dynamic absences correspond to an 010 type screw axis. Okay. How about some others? What we found here, and I pointed that out just when we saw this pattern here, the 110, out in the first order Lowry zone, quite difficult to see here, but in the diffraction pattern much easier, but right there, there's a dynamic absence. And that's at the 10 bar 90 reflection. Right there. Well, you can guess there isn't a 10-9-0 type screw axis available in the space group. That would be crazy to have such. But it certainly could be due to an 001 glide plane going along here that just intersects out here in the high order Lowry zone. So we've got an 010 type screw axis and we've got an 001 glide plane. And we have to remember that they're not unambiguously interpretable. So this is the clearest one that I showed you right at the beginning, right? And that's in the 100. And so that can be either that screw axis or this glide plane here, and both are possible. So DRAT, we can't use that information, right? And in the 010 here, if you notice, there they are, and here. So they can be due to either a 100 screw axis or an 001 glide plane. Both are possible. So these, the clearest, almost the clearest of the dynamic absences aren't really helpful to us. Whereas this one, which is really quite important, is, right? Because it's out there and it says, okay, it can only be that glide plane. All right. So there are several space groups in the that have MMM as the point group that are primitive and have a glide plane containing a screw axis. but only one with the correct rule forbidden reflections that we've picked. Remember, the dynamical absences are kinematically forbidden reflections. So that allows us to deduce that the space group is PMMM. All right, so we know what the space group is now. With Nestor's XEDS, we can tell what the composition is, and we can go be very happy. But we're physical metallurgists, so we don't accept it yet. We're still going to check. You can tell that we're a little nervous about how easy it's been so far, realistically. Just a few diffraction patterns, look for those dynamic absences and so on. Bob's your uncle. So we had to be a little suspicious. So we said, so this space group also has a 100 2-fold screw axis, and we haven't seen that yet. All right, it should produce a dynamical absence in HOO, right, reflections, in the 011 convergent beam pattern, and we didn't see that. In that 100, we saw that peculiar thing up in the first order Lowry zone. But we know, because we're also pretty confident that we got the right space group, we know that this should be visible, this 100 2-fold screw axis. In other words, down the 100 type systematic row. Okay. So there's the 011 diffraction pattern. So this space group also had, right, yeah, we've seen that, right. So the question is, we don't see it here. Why not? This is where it should be, along this here, right? The 100 up here. Don't see it anywhere. Naughty. So, dynamical absences are not observed because of the low intensity and the forbidden reflections. If they're forbidden, they're going to be low intensity. So, what we did was, we meant, not me, but the students, what they did was they tilted to try and increase the intensity of the bar 500, and look what you got. There's the dynamic absence here. And so the screw axis is along here, and so we have a 100 screw axis. So that's the second time we've checked on our work, and we've been correct both times. Now, obviously, I wouldn't have shown you this if it had not been correct, right? So this was an example that shows all the things you need to do probably to get really the right answer and be sure of what you're looking at. Check, 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 all right? And we had 2 checks in that. So we know what the space group is, we know what the phase, the nickel 3 moly, orthorhombic and primitive cell, and lots of information just from several diffraction patterns. And they kind of look nice too, right? Compared with normal diffraction patterns, little white dots. Who needs white dots? We want information, so it's kind of fun. And just from those, what we do here, about 8 diffraction patterns, down just a few, particularly zone axes, and we've got the, so it's pretty good, pretty powerful technique, I think, in terms of crystal structure determination. Here's another example. It's in the days of looking at TIAL and TI3AL and TIAL and so on. And so we wanted to find out what, I'm going this way, what this particular thing here was. And so this was using SAD, of course, here, and you can see there's all sorts of information here about this. But it doesn't tell us much about what's going on. This is, the matrix around here is gamma TIAL, so we know what that is, but this is the unknown. And so we said, okay, how about some convergent beam patterns? And this is the 0001, as it turns out, once we solved the case, but this is the first zone axis. And of course, you're not looking for weird zone axes, right? Because then you're really going to be running up a dark alley. What you want to do is find that ones that are really quite prominent with a fair bit of information. So very clear projection diffraction symmetry here, nice first order Lowry zone there and further out. So lots of information. So the projection diffraction symmetry produced from this was 6 mm. Whole pattern symmetry here is 6 mm. Diffraction group is either 6 mm or 6 mm1R. And I put this in from a paper, as you can see. So the convergent beam diffraction patterns used to determine the point group of the precipitate, shown in figure 2A, here it is, right? And the electron beam parallel to 0001, 0001 of the particle, as we know after we've solved it, showing the projection diffraction symmetry of the so anyway, so we'll plot it. We'll plot it. Or list it properly. I want to go on. So the whole pattern symmetry here is this guy here, the whole pattern symmetry out here. Right, it's 2 mm. The fraction group is either 2 mm or 2 mm1r. How do I know that? I know that from the tables. So that's here. So, did I go to tables here? Right, so from here it's 2 mm. Right, so this is now, I'm looking down the 0001, we get 6 mm and 6 mm1r will be our possible diffraction groups from the symmetries that we see. And I got that from this pattern here. And I'm just skating over this so you can see it. So there's the 6 mm and 6 mm here that we've seen, and the possible diffraction groups. 2 mm and 2 mm here. And so what we have is, these are the possible projection diffraction groups, and then using this table here, you can see if you look up here, so we're looking at 6 mm, sorry, so 6 mm here and 6 mm1r here are those two of the 6 folds that we've seen in the pattern, from the diffraction patterns from the phase. And then, I've got this in the, I'm up here, right, so 6 mm1r here, and 2 mm1r there. So those are two of the things that we saw. These are possibilities, remember. And they've all got to lie in a given point group. And this point group has got the 6 mm. That's a 6 mm there. 6 mm there. But from there on, going down that row, M1R, M1R, MR, there, and then M and M, none of them are there. So it has to be 6 over M, M, M. You're being very naughty here. It has to be 6 over M, 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 which is this row here. So we had 4 possibilities, and the only point group that contains those possibilities is the 6 over M, M, M. Okay. Using the tools right, so 6 over M, M, M. To get the space group, we use the dynamic absences. Where are they? Where the arrow is, there's one there. This is in the 0001 pattern. So possible dynamic absence there in the 3, 3, bar 6, 1. But not sufficiently clear to be certain, right? It would be due to a 10 bar 10 glide plane, that particular one. That's in the first order Lowry zone, right? So it's going to be a glide plane, not a screw axis. This is. How do we pick up the? Well, first of all, what you do is you look in the diffraction pattern itself that you've recorded, rather than something that's on my screen here from the computer. But what's very clear is that you see how the intensity goes in like this, right? So it's dark in there. So, and there's nothing intersecting that. Whereas here, you get the same thing, but look at that, you've got a black Kikuchi line here that's marching through that, so it's affecting that recorded intensity. And if actually, that looks pretty clear over here, too.
Oh, yeah.
Yeah.
You need very good eyes.
It's physicists trying to get their revenge, see? See? Okay. So well, let's take a look at this particular pattern. I'll show it to you here again here. I'm looking at that intensity there. And because I knew that Sudhakar would be here, I then magnified it here, and you can see there's a dynamic absence there. All right, so he does agree. And so we'll say here the dynamic absence in this 1 bar 2, 1 bar 3 reflection is consistent with a 10 bar 10 glide plane but not with a 1 bar 2, 1, 3 screw axis. So it's got to be the glide plane. And so for a point group of 6 over mm, which we've determined, and the inclusion of the glide plane, then we get the space group is P63 over mmc. So it's capable of quite complicated answers, but in very simple physical metallurgy approaches. Okay. How about some other fun? Local lattice parameter determinations. So what we're going to use now is we're going to take a look at these. This is right. We're looking now just for lattice parameters, right, and see if we can see effective lattice parameter changes and stuff like that. So we're going to use then the information that's contained in the Holtz lines, from the Holtz lines, in the bright field disk. So all these Holtz lines in the bright field disk is what we're going to do. And the example I'm going to use, because I like it, is this. So this is a ternary eutectic superalloy. So it's, you know, most of you will know what gamma prime is. You know, gamma is the face-centered version of nickel. Gamma prime is the Ni3Al intermetallic phase, and a lot of superalloys that are used in gas turbine engines contain distributions of gamma prime within gamma. And again, in the 80s, there was a lot of attempts to, how could you really improve that? And so people thought about putting in things like these rods of alpha moly. So every one of these square things is actually a rod, right, a square cross-section rod that's been produced by eutectic solidification. Right? So we're not playing with it and making stuff up. So it really comes out as a rod. So this alpha moly here is surrounded by gamma prime. And then apart from that, there's gamma. So I've got the alpha moly, the gamma prime around it, and then outside of that, there's the solid solution of gamma, the nickel solid solution. So from a high temperature cooling down, the gamma prime shrinks, contracts quite a bit, but the alpha moly doesn't. So this is like me in my old days trying to put my trousers on in the morning and trying to squeeze into them, right? And because things are cooled down and contracted, my trousers are contracted and my big tummy didn't. And so it was a daily routine to squeeze into my, and this is exactly what's happened here. The alpha moly is like, you know, not changing, very stubborn, and so there's a lot of stresses around it here, right, in the gamma prime. Well, that should, we thought, that should change to changes in lattice parameter, because we're putting things under compression then, right, in the gamma prime. The alpha moly just sits there and says, what's your problem, right? And the problem in the old days, I had to get to work, so I had to get these down trousers on. But here, the gamma prime is going to be under stress, under compression, and we should see some effect of that in the lattice parameters that we measure. All right. So the first thing is, what does the gamma prime look like with no stress? Of course, the answer is lose weight, right? So now I'm okay. Now I'm in good shape now. But so here's we've thinned down the foil. I didn't thin it down. Students thinned down the foil until the alpha moly just dropped out. So alpha moly dropped out, so then there's no more constraint. The gamma prime is just completely relaxed. And then we measured then these diffraction patterns. So this is the 114 zone axis, seabed. So it's a disk, but the important information here, the Holtz lines, the high order Lowry zone lines, are here. And here's our simulation of them. And this is a kinematical simulation of these, right? No fancy dynamical theory. And you can see, if you compare those two, they look pretty good, right? Now, obviously, what we've done in the simulation is we've changed the lattice parameter, right? So it's Ni3Al, so it's a cubic, right? So it's got A equals B equals C. We just change the lattice parameter until we get a good fit between this and this. And then we can say that our lattice parameter is about 3.57. And that's about as close, about as accurate as you can get with diffraction. If you want to get better than that, you have to go to X-ray diffraction, right, as we know. Okay. What's important for us, though, is this. If I look down here, that is actually a mirror in the 114. And so I should see everything here should be the mirror of what is over here. And is it? The answer is yes. So excellent news. This is an unstressed piece of Ni3Al. And we've shown that now because our diffraction pattern shows that there's a mirror here, as there should be, and we get a good fit with this as our 3.57 angstroms. So we could tell immediately what the volume of the unit cell is when it's unstressed. So we'll know that as well. Just take the cube of that number. Okay. Then, this was Mike Kaufman who did this, who's now the dean at Colorado School of Mines. He marched around here. Here's the alpha moly back again. So we know this stuff out here, the gamma prime is under compression now. And we marched around, he marched around and took a diffraction pattern there, 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 and there. So, and there. So one close in, one far away, one on the diagonal, one close in, one far away over here. And then you simulated these patterns, and what you're going to see is start with this one here, one that's close by. You can see that there's already a break in symmetry here. You can't put a mirror down here, a mirror axis here, right? And you can see it more clearly in the simulated version here. And then if I move further away, it starts to look like it's almost getting back to being like the unrelaxed condition, but not quite. So there's more distortion here than here. And we're able to kind of quantify that. It's kind of cute. Think about it. Same thing here. If far away, our break-in symmetry is very, very little. It almost looks like it's not a problem. But when I get in close, though, to the alpha moly, where my stress is going to be higher, then you can see that the break-in symmetry is, just take a look at that. Break-in symmetry is more clear. You see this intersection here? That should be in the middle of these two lines here, but it's over to the right there. And this one was over to the left up here. So what it's telling us is that we're getting a variation from near the alpha moly itself, where we imagine the stresses are highest, coming out here, and we're picking that up. Down the diagonal, it's basically nice and undistorted. Because what I've got is I've got one sense of stress this way, the other stress that way, and they cancel each other on the diagonal here. And we pick that up as well. So it's very sensitive to these lattice parameters. And we're just using, at the moment, we're doing two things, right? We're using our eyeballs to look at the symmetry and the symmetry breaking, and degree of symmetry breaking. And of course, we've got from these simulations, we've got what the lattice parameters are. So here are these lattice parameters, A, B, C, and you'll notice that they're different there. So 3G is this one here, A, B, C, G, yeah, so it's talking about the simulated one. So this guy, the same as this guy here. All right, so that's the local lattice parameters, and you can see we can do this all the way down here. And so we say the A lattice parameter is much larger than the unstressed value, as expected, but B and C lattice parameters are either smaller or similar to the unstressed material, but at least one should be larger. And here's the key. The volumes of the unit cells are 45.5 angstroms cubed, that's the unstressed. And for the four other cells we've got in the table and the data, it's 44.5, 44.56, 45.61, 45.75, basically the same. So we've got different lattice parameters, we've got almost the same unit cell volumes. So what it's telling you is that this is not a true representation of the state of stress. It's an indication, but it's not a true. So something else is happening. And what else is happening here? What's happening is that we made a very thin foil to get this data, And so when you have surfaces that are fairly close to one another, you have surface relaxations. And so the surface relaxations going around here are varying, but they're allowing the unit cell to be at the same volume. Why? Because it wants to be. That's why the equilibrium cell value for our unstressed condition is the same as these guys here, because what's happening locally is our thin foil is varying in relaxation to allow us to get to an equilibrium value. Is that cool? Is that good? No, it's not, because it means it's not telling us the actual number. Right? We're getting a qualitative bit of information here, but we can't say that it's absolutely the correct one. Now, before we start feeling sad about ourselves, imagine everybody doing very thin samples for high-resolution microscopy and getting information that may or may not have any physical meaning, because you're going to get surface relaxations there as well. So this is one of the problems in electron microscopy. We make thin foils, and so we can get things that happen that deviate from the actual physical reality, because in the physical reality, all that material is constrained. Whereas now we're allowing it to relax a little bit. So you can imagine the downer of getting this information and saying, yeah, we've got it nailed, and then getting these unit cell volumes and going, oh, this is all also just doing something about the stress relaxations that right, being physical metallurgists, we can't calculate that very easily, right? How much that is occurring. But it means we have to be very careful how quantified we want to be with this technique. So, the results may be interpreted on the basis of lattice relaxations afforded by the proximity of the foil cells. And so here we are in partially crystallized Udimate 720, and this is another superalloy, and we say in this relatively thick region here that we're operating, there is a distortion from cubic symmetry. Our single mirror is broken. You can see that there. That intersection should be in the middle here. It's to the right as I'm looking at it. If you go to the right to the very edge, it's gone cubic on us. Right, it's lost that change. So what we know is if we want to get close to the truth, we have to go to quite thick foil. And as you know, quite thick foil is not always easy to work with, because it's dark and dingy and you can't quite see clearly, and there's a lot of phonoscattering in the background of the diffraction patterns and so on, so it gets less clear. But whereas you might say, this looks really cool, and this looks more grungy, this is actually more representative of what's happening in the Udimate 720 than is something taken from near the very thin foil edge. So that's just a watch out scenario. So we say in this relatively thick region, an orthorhombic symmetry is observed, and that's where I got this pattern from. Remember these dynamically split lines? So there's obviously, this is thinner, that's a little fatter, and that's the fattest separation of those lines. So clearly then we have not a cubic, not a tetragonal, an orthorhombic symmetry is observed here in this pattern. And we say the various results demonstrate that relaxation in the proximity of foil surfaces and the influence of various components of the microscope can influence seabed pattern symmetries, and hence extreme caution is necessary in interpreting the results. So when we say thin foil, how thin? How thick should we get? So we did experiments looking at, there's another period where my really good pals in physics were going bonkers over these superlattice multilayers materials. And they'd be things like silicon, germanium. So germanium alters the lattice parameter in silicon. So if you have silicon and then the next layer would be silicon germanium, then you'd get a difference in lattice parameter of the silicon. Say if you had 5% germanium in there. And so there had to be a strain at this interface. And this was in the early days of high-res microscopy taking off. And a fellow called Murray Gibson at Oxford University made the proclamation that anybody who thinks there's strain at these interfaces is an idiot, because we've seen in the high resolution, high voltage microscope that there is none. What he didn't realize is that the thin foil relaxations were just getting rid of that distortion. And we did experiments looking through microns of silicon, and we still saw this dissipation of the strain. So it's a really, you can look through quite thick foil and still see a manifestation of strain relaxations, stress relaxations. So it's important that one bears that in mind. I think Nestor talked about this, so this is using the seabed information with these Holtz lines and with these two-dimensional information in the bright field disk and these fringes, and so I think you've seen that. So I say, let me finish up by saying, seabed is really useful for crystal structure determination. You can get unambiguous responses. Local lattice parameter is very effective in local lattice parameter, but it's of the sample you're using. So if it's a thin foil, it will be relaxed, and therefore not the same as you could have something in bulk. And if you want to get some information about the bulk, and you make a thin foil, you've got to realize and remember, you might well be getting relaxations that are changing the answer, right? So you have to be very careful about that. So this is rock solid. This is, you've got to be careful with this one. And then the other things I haven't looked like little peaks at the dispersion surface and so on. That'll be, next time I'm here, I'll show you that. But as for that, I will wrap up here. Thank you very much.
For high symmetry materials, I mean, the lower the symmetry, it'll become more and more difficult to work with, isn't it? Or
Yeah, but it shows you that it's not a high order system if it gets difficult, right?
huh.
But it's still, you've still got all the diffraction evidence there.
Okay. So, but it's
So it doesn't hide anything.
okay. Yeah.
Yeah. You have less information to work with.
But it's a useful technique whenever you have a small crystals that you can't pick up in the X-ray diffraction, isn't it?
Yes.
That's the beauty of this.
Yes. So X-ray diffraction is highly kinematical, mostly. And electron diffraction actually turns out to be mostly, a lot of it, dynamical. And so when I showed you a lot of our calculations were kinematically based, actually the best thing to do is to do them dynamically based, and then you can get the whole Monty is available then. So find a good friend in physics who will help you do that, right?
So other questions?
I think they've had an overdose of lecturing today. Sleepy. Well, if you think of questions, I'm back here tomorrow. Promise I'll be here all day. So no running to hospitals. Good.
No questions today? There are no questions, then we'll wind up tomorrow morning. We'll start at 9.
Oh, that means you have to leave 7:30 from the hotel there to get round. Yeah. You can see the campus from the hotel, but the roads take you a sightseeing tour around Chennai to get back to the campus.